Hi, Valerie.
Hi, how are you?
Good. How are you?
Doing good.
I was just beginning to wonder if I was in the right Zoom room, but yeah, okay.
Oh yeah, I know. I figured I would join a bit early,
No,
just
no,
to get the mechanics down.
no, I started it quite a bit early too. So yeah, I had a little problem yesterday with the YouTube stream. So
Oh,
I see the now.
I know. Yeah, I changed my laptop today. Usually I'm on Linux, but I wanted to use PowerPoint, so
Gotcha.
I had to do the same thing, little tech check.
Yeah. Hey, Bia. Hey, Lindsay.
Hey, how are you?
Good.
I thought I was late, but no one is here yet. I'm surprised.
Yeah, I was the only one for a little while before Valerie joined in.
Hey, Valerie, how are you?
Good. How are you, Bea?
Good. Did you like the workshop yesterday?
Oh, it was amazing. I was blown away, honestly. It was incredible. And
It was fun.
seeing everyone get so excited about Steve, I love it too.
That's
I
awesome.
had a funny comment from Laura Brandt, who came from with Liz,
Yeah.
and she said that she kept hearing Sarah instead of Sarah. So it was like Steve and Sarah. And I thought that was so funny.
That's cute. Yeah.
Yeah, because we always talk about Steve like he's a person.
Yeah. So I told you in Slack that I have like 35 slides, and I'm not very comfortable with some of the data because it's out of my realm of expertise. So I am nervous today. I will need help.
Is there an official Steve Slack channel?
No, it's only for the organizers, so we don't
Got
go
it.
crazy.
Fair enough.
How are you, Lindsay? Good talk yesterday.
Oh, thank you. And no, it wasn't. I gotten panicked like partway through the beginning, and then I was like, oh no, like I have too much to talk about, and then like I think I made no sense at the end. But I appreciate you saying that it was a good talk. I don't believe you though.
It was good.
It's funny how everyone thinks that about their own talks, is they're like, oh, that was terrible. But from an outside perspective, we don't know what you were going to say. So we thought what you did say was great.
Okay, cool. Fair enough. I guess what I compared it to in my mind, what I was hoping it would be, wasn't quite. But as long as it came off good, then that's good. Yeah.
Yeah, I think you're the only one who has that expectation. I'm the same way for present. I think everyone is. Yeah, that's why we get nervous, right?
Have you ever recorded a talk? Have you ever recorded a talk?
Me?
Yeah.
Like I've recorded talks, and like it takes forever to do them. Like I'll spend the whole day just trying to have like the perfect like recorded talk.
Exactly.
Like,
yeah.
I hate my voice sounds, I think, like a little kid on voice recording. So when I hear it on the phone or on the voice recording, I'm like, oh, it sounds like I'm so young.
I think that's for everyone, not the young part, but I don't like my voice at all. At all. There is no other sound that is more annoying to me than my own voice.
Same with me. Like my voice is so annoying to me. Like
I think your voice is awesome. You can stand up in a room and everyone hears you. It's amazing.
Loud.
I'm loud,
but that doesn't mean it's a good voice. Foghorns are quite loud.
But it's not
too.
loud. It's like the capacity of projecting your voice. It's like, wow, that's like special power to me.
Oh, thank you. But I still, I don't like it. I like it. It still sounds obnoxious to me. Foghorns can be loud, like it's my perspective. But thank you. I appreciate that. I think everyone here has a nice voice for what it's.
Did you ever do any theater where you had to learn how to project your voice like that?
Not really.
Oh,
no,
I was going to say you sound like theater training. I know a lot of my brother and sister are not STEM related at all. They like movie director, arts, and everything like that. So yeah, they kind of do more play stuff.
That's super cool.
I feel like the technique for speakers is pretty similar though. Like it could be applied for theatrics and for science.
Hi, Evan.
Fair enough. I think there should be more training in like how we give presentations and stuff like that. Like Bea and Bill Archer, like a few years ago, at CEDAR gave like a good like how to give like a good presentation talk, and we should have more things like that of like how to like make clear points and like like how to present.
I have forgotten about that, but that was a fun talk to prepare with Bill. I think it's the first time we gave a talk together.
It was a good one.
That was cool.
I'm getting a little worried that no one else is here. Was there like multiple Zoom? Oh, Evan's here. Okay, so at least one other piece. We got Evan.
There's only one link, so you're in the correct
Okay.
one.
Good.
So I'm eating lunch, so I had myself muted.
Oh, no problem. Yeah, I had to, I did the same like half an hour ago. So today we don't have Benji, at least for the first session. He will join as soon as he's back from his appointment. Hi, Phil.
Hello, everybody awake?
Partially.
And I'm not in Central European time either. Oh, there's Emma. Oh boy, you get such credit for.
Yeah.
Here I am complaining about being tired. I will stop complaining completely. Emma, I spent a good deal of time up in Kiruna, and I've been to Sodankala a few times. And I have friends up at SGO and the Finnish Meteorological Institute. And I still can't pronounce, unfortunately, Finnish anywhere near good enough, so I don't try. So I appreciated you teaching us a couple of correct pronunciations yesterday. That was really it's the A that gets me. I don't know.
Yeah, when we were working with the Dunes paper, we joked a bit about using some Finnish name for the dunes, kind of in a Steve-ish fashion.
I think you should have. I think we would all have learned to deal with Finnish a little bit better. Yeah, it's a really interesting language, and I you know, my last name is Eriksson, but my Swedish is terrible, but it wouldn't have mattered even if I knew more Swedish than I did. Yeah. Finnish is just it's so different. It's just fascinating to me.
We've been kind of scared that one day only also Icelandic aurora observers might find something new and name it according to their namespace.
There we go. Then we're all on the same playing field. Wow, that would be great. I'll tell you, when I was much younger and kind of just fooling around with a radio, I had a shortwave radio. In fact, it's over here. And I used to tune into one of the Canadian broadcasting services, North services. They would have shortwave links because they couldn't, not enough money, and they would do a half an hour program in Inuktitut and a half an hour program in Cree every day. And I could just turn that on and listen to that for the whole half an hour. I had no idea what they were saying, but the language was so beautiful that it was just lovely to listen to it. It's so much more musical than a lot of the Western languages that we use. And it was just marvelous. So I appreciate good languages.
Who do you know at Sodankylä?
Markku Lehtinen was there for many years, of course. Esa Turunen, hung out with Esa a bunch of times. Thomas Ulik, of course, who's there now. And Juha Virinen, who came out of Sodankylä and is now in Tromsø as a professor. So, yeah, we have a lot of friends up there. It's a great place.
Yeah, I've talked with Thomas Ulich, and he's also an active Skywarden user.
Yes,
which I didn't know.
Thomas is very, very energetic, and that does not surprise me at all. And I didn't see Aurora at all sitting by the Kitanen River. The one winter I was up there, and I'm like, perfect, and nothing. It was KP 0. Still waiting. That's why this conference is great, because I get to see things that I wish I had someday.
the next one we need to organize it then in a place where we can see the aurora. I have never seen it either.
Totally. Resolute Bay.
So.
Let's try to get everybody on a C-130 and get him into Resolute Bay. I think, Bea, that would be our next logistical challenge. Oh, thanks. Oh, all right. I guess it's a little after two. Well, not very much, but it is a little after 2, isn't it? Yes.
And if I remember correctly, Carlos is here late today and Gareth had
I
office hours.
I believe that is true. And we had, Bea, we had you and Bharat as the moderators today, right?
Yes.
However, I think we were gonna just briefly spend a minute or two just talking about some of the things that we discussed yesterday, right? Just as a reminder. Oh shoot, I closed the window that had the summary, some of our notes that we were taking.
I can send it to you in Slack.
Yeah, okay, thank you. So yeah, folks, our idea was just remembering just some couple of points that maybe stood out to at least some of us from yesterday. And then just as a reminder, for day 2 here, we have Toshi Nishimura leaked over from yesterday because we had such energetic discussion that we ran out of time. And then I think we were going to hear from some modelers here. And I know, Valerie, you were going to talk a little bit about AmGeo. And then we were going to have a discussion, really. I think our phrase was kind of what to model and how to model it. That was kind of where we were going to go. And then the break at the usual time at 5 p.m. Eastern. So that would be 2300 UT. And then the second block is going to be led by, I mean, Bea has a list of campaign events, and we're going to dig into campaign events, citizen science, simulation of events, and then just discuss how we can proceed with analysis of those, I think. So that's the plan for today. And now I will go and get the link and spend a moment or two, maybe just discussing. And I would like our other conveners here to jump in, please, and tell me whatever they thought also that I forgot. Looking over this last evening, it was very clear. I mean, the citizen science stuff, we found there was, of course, unbelievable amounts of potential and unbelievable amounts of information. We did see, I think there was a clear indication that resources spent on getting that indexed and with good metadata and exchange of that metadata between people to search for interesting events was certainly a good priority that we could pursue as a community, I thought. That came through very clearly. Things like Liz McDonald pointed out that, you know, there are other experiences with communities that are trying to do this, especially with regard to large citizen science collections, but that requires volunteer management and planning. And then software happened to be a particular challenge if you're talking about resources that could be accessed there. But people like NASA were wiring in citizen science in large to small missions so that there was an opportunity, we thought, to connect some of this work. And I would say that the other thing was, aside from the sort of summaries that we gave about various instrument capabilities, there were at least a couple of mentions about timing of all of these various events, what came before what, and under what conditions may that change. There was a very strong admonition, which I thought would be useful to think about, from people like Brian Harding and Josh Semeter, to be careful about our preconceptions that we brought into this. Just because it looks like something that is field aligned, for example, doesn't necessarily mean it is. It just means that that's what we're carrying in, and we ought to do the good science thing and back up and just see if we could verify that our assumptions were correct, and keep an open mind, right? Be willing to adapt to a new piece of data, maybe from a citizen science photograph that shows us, whoops, okay, we didn't understand that. And the last thing I'll mention is just the notion of time scale. That it was obvious that in many, many things in geophysics, the better you observed in terms of time cadence, the more features you started to uncover that were perhaps writing on top of a larger envelope that you just didn't know were there because your instrument didn't do that. And I thought that the camera capabilities that people are carrying into this, even in a broadband sense, not in an ultra precise spectrograph exclusively, were also very scientifically useful. And, you know, Josh gave a great example of that. Carlos gave a great example of that. And that those are ways to use our tools in to add new dimensions. Again, if we don't limit ourselves to say, we got to have a narrow slit spectrometer on that very spot, otherwise we don't know anything. We do know things that we can look at from the large scale as well as the small scale view. So those are some of the things that I saw that kind of kept coming up again. Do any of the rest of you moderators want to add to that?
You're right. That sounds exactly like I was thinking. And also I like the comment by Brian Harding yesterday that he brought to the attention of, can we really distinguish using only red line images, whether or not we are observing a SAR arc or a Steve? And that is an excellent point. So that's a very tricky question to answer without having the spectrograph data with that data set. But that question is there.
Sure, I agree with that. Okay, so if I'm going to turn it over to Bea and Bharat here in a moment, the only thing we forgot to mention at the beginning of this, and we'll discuss this tomorrow, okay, toward the end of the workshop, is that in addition to making some concrete plans here, we hope, about what to analyze, we are also going to think about what people might want to write some articles on what we're doing. That includes popular press articles, by the way, and figuring out what the best ones of those are to increase exposure and trust in the community about what we're doing. And we're also trying to capture some notes here that will go into both the report that we send to NSF on this particular workshop. And in the US, there's a decadal survey process spinning up in geophysics. This is a, as the name says, once a decade thing, and they solicit white papers, focused papers on, hey, we think this is an important topic for these reasons. And we feel that most of the information we're gathering on this conference makes a perfect white paper and from the community. So we'll try to see if we can inject that into the process there. That gets the attention of funding agencies because they tend to try to use outcomes from that process to dictate announcements of opportunity and stuff like that. So remember that the information we're carrying in here isn't just living in this workshop, and we just wanted to reassure you that. Okay. Bea and Bharat, you got the controls and have at it.
Awesome. Our first talk is by Toshi Nishimura. Toshi, are you ready?
Sure, let me try screen sharing. Let's see, one moment. I'm on a new computer, so probably need to work on the setting. Yeah, so one thing I wanted to add to the points that Phil was making was that we need to understand things like how the SAR arcs evolve into Steve, vice versa. So there are various miniature processes going on, and we need to place Steve into the context of what we know, also what we don't know. So that will be a real scientific challenge for Steve, but great potentials for doing lots of interesting research. And it says I need to launch Zoom again, so bear with me for one moment.
Okay.
Sorry about that.
No problem. To add to what Toshi was saying, it's also, to me, this is also a bigger question in the community, since we know that there is a relationship between SAR arcs and SAPs and Steve and SAIDs. This could help us eventually understand a little better the relationship between SAPs and SAIDs.
Oops. Hopefully I can share screen now. Sorry, I just switched to a new computer, so I'm still learning. All right, so So yeah, I also enjoyed the discussions yesterday quite a bit, and I wanted to contribute to today's discussions, which are the modeling and events, campaign analysis. So why do lots of data analysis using various instruments? But those are the things that provide the information for the modelers to drive their models, knowing what magnetosphere is doing, and what kind of ionosphere responses are happening, and why Steve is so special compared to other things. So yesterday we saw Liz McDonald's paper showing beautiful swarm observation of SAID, strong heating, density depletion. But we need to know more in order to really understand what's going on in the MI coupling system. And also Bear has shown that Steve is almost always related to substorms, particularly happening during recovery phase. Why it's in recovery phase and why Steve is so rare compared to the number of substorms. So there can be lots of substorms every day, but Steve is happening only several times a year. So obviously magnetosphere is involved. What's going on in the magnetosphere is an important question, because sometimes intense SAID is happening, but oftentimes such fast flows are not there. We end up with just regular SAPS flows. So this is one of the campaign events that they are selected. So there's a beautiful Steve forming equator of green diffuse aurora that's going to be showing up right here over Alaska. And the magnetic midnight is this blue line. There are lots of diffuse aurora happening in the auroral oval. So this event starts with a substorm onset in central Canada near midnight. An interesting thing here is that the substorm expands very quickly to Alaska, and then the Steve appears in the Alaska sector. So let me play this one more time. The substorm activity is here. Not much going on in the Alaska sector except for this diffuse stuff. This is proton aurora. Then the proton aurora dies away, and then that is taken over by Steve. So there's an interesting transition going on between proton aurora and Steve, and that is associated with the substorm activity quickly expanding to Alaska. So now the center of the substorm activity is not at midnight, but very far away from midnight. And Steve appears to form at the longitude of strong auroral activity at higher latitude. So that indicates the important magnetosphere activity shifting across several hours of local time. So this is at AU and AL indices of the substorm event. It starts around 6 UT. The auroral activity is clearly seen initially at high latitude, not much going on except for this diffuse proton aurora stuff. And then later on, when the surge appears over the Alaska sector, then the equatorial boundary or oval sun shifts equatorward, and then the Steve starts to appear, and it nicely follows the equatorial motion and the poleward retreat of this equatorial auroral boundary. And so Gareth mentioned this yesterday. This was one of the events where we have the fortunate super echoes in the Steve area. So this is the Steve arc we saw in the previous movie. And strong flows toward the radar and away from the radar can be seen from these two super radars. So that's the SAID narrow flow channel, and that starts right before the appearance of Steve. So SAID starts maybe 5 or 10 minutes before, and then Steve starts to appear. So there is a potential causality between these two. And then this kind of beautiful emission appears over here. Then there are lots of small scale structures, including picket fence, going on in this event. So we have the MSP spacecraft flying over this area. So let's look at some ionosphere observations. The left column is the data before the substorm. That's a pretty typical thing. There's a trough. In this case, there was not much flow. We typically see weak SAPS flow in here. Not much heating going on yet. The electron precipitation cuts off here. So this is the equatorial boundary of the oval. This is the equatorial boundary of the ion precipitation, and that's the area where we see the downward region 2 ferrite current. So there's nothing special going on at that time. And then the next two columns show the Steve observations. So both spacecraft fly over Steve in a little different longitudes. So this is pretty narrow, deep trough, and that's exactly where the CID is sitting. A strong electron and a little bit of ion heating going on within the flow channel. The electron precipitation cuts off here, and sometimes, though not always, we see some soft electron precipitation going on. The interesting thing here is the ion precipitation decreases, so at least within this energy range, there's no substantial ion precipitation here, even though the substorm is going on. And the region 2 became really narrow. It's only happening within this area that's comparable to the longitudinal extent of SAID. So the magnetosphere driver gets confined to this region, and that explains why the SAID, a fast flow, was confined to this narrow latitude range. Pretty much the same thing happened for the satellite. So in this case, this satellite measured double SAID, a little wider heating, then a little bit of soft electron precipitation here, and reduced ion precipitation. The electron flux has gone up quite a bit. So you can see some electron acceleration happened during substorm, and region 2 became intense, but confined to the latitude range of SAID. We have done some superposed epoch analysis to see whether what we saw in this the previous slide can be generalized, and it appears to be the case. So the top panel showed the precipitating electron flux integrated over energy. The left column is before the Steve occurrence. We saw the substorm growth phase or expansion phase. The right column is the substorm recovery phase when Steve was happening. One obvious thing here is that the electron flux goes up and the boundary became sharper. So the conductance gradient became steeper. So that coincides with the formation of SAID. Sometimes there can be double SAIDs. So that's a striking difference from SAPS prior to the emergence of Steve. The electron heating can occur even before the emergence of Steve. The previous event didn't have it, but sometimes we see electron heating that can be comparable to the electron temperature that was measured during Steve. So electron heating itself may not be a good indicator of the Steve occurrence. The ion temperature is substantially different. The ion gets heated even at the MSP altitude. So probably due to frictional heating, when a strong flow happens, frictional heating occurs, and then that triggers the Steve. So that seems to be the scenario we see from the MSP measurements. So the real question we need to ask is why that difference happens, what's going on in the magnetosphere. So we turn attention to the magnetosphere measurements. So these are two Themis spacecraft measurements in the inner magnetosphere around 4 radii in the preliminary sector. On the left, we see a very distinct SAID flow. On the right, we see a broad SAPS flow. So this was kind of saying what Evgeny and I were discussing yesterday. So why there can be some differences. So one major thing is that the plasma pulse becomes really sharp when SAID happens. And the electron flux gets really enhanced and sharply cuts off right around the plasma pulse. When SAPS happens, the electron flux gets enhanced compared to the pre-substorm level, but it is still lower than the electron flux when the SAID is happening. In terms of the ion flux gets enhanced in both cases, but the ion flux cuts off right earthward of the electron boundary when the SAID is happening. So this is the only area where strong region 2 can be driven. While for the SAPS situations, the separation can be wider. So this is a pressure gradient. The ring current So the region 2 field and current can form within this broad L-shell range. So the latitudinal extent of the region 2 driver is quite different, and the energy of the electron as well as the flux gradient is quite different. So that seems to be the important indicator of the SAID occurrence. And so we have discussed this with Frederickson quite a bit, and we're doing a statistical study of this using THEMIS and Van probes data. We have identified SAID and SAPS as close as possible to the ionosphere definition of SAID and SAPS. We have identified 200 SAID and 130 SAPS events, and we have done superposed epoch analysis of them. So this is just showing that we have a pretty good event list of SAID and SAPS. So one clear difference is that SAID is narrower. Of course, the flow is faster, and these very fast ones are probably the intense SAIDs. The SAPS is weaker and broader, so typically the width is twice as large, but it can be even wider. Okay, so with that database, let's see what we can learn by looking at other parameters. So the middle panel is the electron flux integral over energy, and the last panel is the ion flux in the same superposed epoch frame. So one interesting difference is that, like in the case study shows, the electron flux it has the bigger gradient for SAID cases compared to SAPS cases. So the flux values are quite a bit different, and the gradient is also different. So that indicates that there's a sharper conductance gradient for SAID situations. And also the ion flux sharply cuts off right earthward of the SAID, what the inner edge of the electron boundary. So again, this is the only area where we can drive the strong downward region 2. So that explains why the flow can happen only within the very narrow L-shell range. And that's very different from SAP situations. The ions can be injected deeper in, so the broad downward region 2 can happen over this area. So some substorms create this, other substorm creates that. So whenever this is happening, there's a chance that we get the intense SAID, and then that is probably a condition where the steep can occur. Just quickly, the density gradient can be sharper. So the sharper plasma pulse for SAID cases and SAPS cases. The low frequency waves are also enhanced. So it seems like the faster flows are triggering instabilities like kinetic alpha waves. So those are probably the sources of waves that if-gain emission is talking about. The explanation is that so we have done a Rice convection model simulations with the Rice University group. And so the basic idea is that, so the sign is to the left, if we inject the plasma from midnight, we will get the usual situations where we see SAPS flows. These black lines are the equipotential contrast. And the background, the middle part of the ion density, the right column is electron density. The electrons are not coming to the dusk side, so we just get the ion pressure enhancement. So that's where we get SAPS. So that's a pretty classical understanding of SAPS. But for steep situations, we get a lot stronger electron injections, and aurora is moving far away from midnight. So that means the reconnections and particle injections are happening at pre-midnight. So that provides a direct access of electrons to pre-midnight. Notice that the electron flux is quite a bit different compared to the midnight injection cases, even though the strength of the injection is the same. So that increases the conductance in this area in the ionosphere. So the SAPS flow gets really narrow in this region. So that's why that intense and narrow SAID flow channels form in this area. So, so that seems to explain why strong heating can happen when strong aurora happens over the pre-midnight situations, and that was probably the preconditions or the conditions to create Steve. Yeah, and so we'll hear lots of discussions, how these things can affect the ionosphere from mooring. So I look forward to those discussions. So basically what we have found so far is that the magnetosphere condition is very different to electron injections, the auroral precipitation, the conductance gradient, and the size of ferrone currents are a lot different from non-Steve events. So these conditions can explain why intense SAIDs, narrow trough, and strong heating can happen when Steve is happening. So the question is how to create emissions from here. But in terms of the magnetosphere conditions, I think we have some understanding of why the magnetosphere is special for Steve events. And the superpositive Fock analysis, the magnetosphere supports what we see in the ionosphere. Yeah, that's it. Thank you.
Thanks, Toshi. This was excellent. Any questions for Toshi?
Liz has a question in the chat. So Liz asks, double SAIDs would be fun to discuss later too, and as an edge case, maybe useful clue. I wonder how many there were in the statistical study, and could you say how much time was covered in the statistical satellite data that found 200 Steves?
Yeah, so yeah, that's a great question. So yeah, double SAID is pretty common, even though not always happening. So as you can see, SAID peaks are often happening in two places. One is just the equator of this electron, the equator boundary, and the other one is like a degree or the 1.5 degrees equator of the electron precipitation boundary. So it is still a question why it can be double sometimes, and in other times it becomes single. That's in either case, a steep can happen. So how often this is happening is a question I still don't know how to answer. It is not easy to collect these events because when we have done this study, I had pretty strong event searching criteria where Oscar imagers cover the whole sequence of substorms, so we know the data before the Steve occurrence, so we can see the difference between those two. So we didn't have too many events, but once the Steve database is evolved, then hopefully we can accumulate more events.
Thanks, Toshi. I think Phil has a question.
Yeah, Toshi, and I don't know if we had discussed this before when we discussed this earlier, but in the two cases of SAPS versus SAID, if you integrated over, you've obviously got more intense region 2 field line currents in that left-hand side, which you're pointing at right now. But if you integrated over the region, okay, is the current going to be more intense when you integrate it over that region for SAID and less for SAPS? I'm trying to, I carry numbers in my head about the, current density for SAPS, but if it's higher for SAID, what about for the whole region? I just wonder if it's a fundamentally different coupling situation.
That's a great question too. I think the total current may be about the same because, if you compare the level of the ion flux for SAPS and SAID, it's not really different. It can be even smaller for SAID. So, if you think about the total pressure gradient over, say, 1 array distance, it can be about the same. So we don't need to have a stronger ion injection to create stronger flows. So what I think is we need a stronger conductance gradient. So, the sharp gradient of ion flux is confined to a narrow region. So that creates a narrow downward region 2, which we see in here.
Right. Okay, that makes some sense. So if you're thinking about the picture of the electrons and the ions being separated and, that difference causing the coupling, that would be an important principle, I think, to point out to people who are trying to put these two in their minds, rather than to say, it makes them both kind of versions of an event, if you want to think about it like that.
Yeah, so that's, that's one of the reasons why I was making the comment earlier. So we need to put the Steve into the broader context of subauroral inner-ionosphere coupling science. So we know we have studied SAPs, SAIDs, injections, trough, and so on quite a bit, but we still don't have well accepted answers about why SAIDs can happen in certain conditions, why SAPs can happen instead of SAID, what's going on in the ionosphere. So by studying Steve, we will be able to answer those questions. So that's will be the contribution to the broader science in the German cellular community.
Right. Thanks.
Thank you.
Matt has a question, Toshi. Matt, can you?
Sure.
Hi, can you guys hear me?
Yes.
Yeah.
Okay, good. I have a question about, I think it's the next slide, the epoch. Yeah, this. So I have a question about the energy, from doing a lot of modeling flow channels and auroral arcs and things like that. It's pretty hard to have 1-2 kilometer per second drifts without having a lot of frictional heating in the ions. So I just wanted to point that this is kind of unusual. Is the ion heating bottom right? There's really not too much in the way of an enhancement. And if you back a slide, sorry to make you bounce around here, but if you look at the red crosses in the two Steve cases, there is some missing data there, but there's just not a lot of enhancement. My question is really twofold. A, what's going on with the ion temperature, and B, is this dealing with a large uncertainty data here? It's simply the case that the ion temperature can't confidently retrieved, or do we have some unusual physical situation where it's just not enhanced the way one might expect?
Yeah, so this is a difficulty of getting that precise distribution function measurement. So yeah, I think the ion temperature is underestimated. So we have a tendency, we see a hint that ion temperature can be larger here, but we don't have data. That's because data looks like this. And one reason is the density goes down and the composition changes. The oxygen is no longer the major species in here, but the oxygen is a species that the MSP cares about in terms of getting the moments. So if the oxygen dominance assumption breaks, then we can't get the good moments. So that's why there are data gaps. So we see a hint of a temperature enhancement, but it can be larger than what we see in here. At least we see that the temperature is higher than before.
Yeah, right. There's some hints of structure there. I guess so. Does DSP rely on some specification of ion mass or ion composition? I don't know enough about the instrument.
Yeah, they assume O+. So if O+ is not the major species, then the flow
is coughing up a bunch of molecular stuff. It's going to mess with the analysis. And that affect both the ion and electron temperature or just the ion temperature?
Well, the electron measurements also affected, though not as severely as ions. So sometimes we don't have the good electron temperature data either. In this case, we have relatively good measurements. We do know that the electrons got heated. So like this data gap for the velocity is also because of the low density and low oxygen concentration.
Right.
So those are still challenges.
Yeah. I mean, the same problem with the ISR when you're looking at these high temperature regions, there's never that much plasma there, and so you have all this large uncertainty. But okay, cool. Yeah, not to get into the weeds, but when I show some of the modeling stuff, I think the temperatures, at least that I'm getting out of some of my simulations, are almost unbelievable, fully unbelievable. But you'll see when I show them.
All right, we can quickly move to Carlo. Sorry, Via, I didn't mean to.
I was going to do the same. So
Yeah, we can quickly move to Carlos's question. Then.
Okay, yes, thank you. Very nice, Toshi, as usual. You have one slide in which you have to the left SAIDs and to the right SAPs, and you have a window where you're defining them. Maybe, yes, there, maybe I missed it. But if I were looking at the SAPs, it seems like your left band or left line is very, very to the left. So if I were to say, oh, I see a SAPs, I will go much farther to the right. So what is the criterion in which you define SAPs? Also, the plasma pulse seems to be closer to the right line.
Yeah, so you're right. I should have drawn the left line over here. So the threshold I had was 3 kilometer per second. So these are really not SAPs. I meant to locate the inner edge of the ring current, which is the inner edge of the ion injection in here. So this was not the SAPs inner edge. Plasma pulse. So there are multiple gradients. So in this situation, the plasma pulse is harder to see. So the major one will be here, but this was not meant to catch the plasma pulse.
Oh,
but
okay.
This was just a certain value of the integrated electron flux to define the inner edge, so you can start see the loss of the high energy particles. So the electron flux is suddenly dropping in this area.
Okay, thank you.
Thank you.
Bill has a question.
Yeah, I got a comment, I guess. One interesting thing to do could be to look at DMSP, a comparative analysis with DMSP measurements over flow channels in the polar cap, which also have signatures that aren't that different from this. High electron temperatures, very little ion heating at DMSP altitudes. And we've always, including the paper that Toshi and Matt have been working on with us, we kind of assume that the electron heating is top down, right? It's coming from the magnetosphere. And it seems to me the working hypothesis here is that that's not that clear with Steve, where the intense electron heating is coming from, maybe a combination of both. So it's just a comment, I guess.
Yeah, thanks for the comment. Yeah, it's interesting to look at polar cap data. Yeah, there can be flow channels, particularly when the polar cap arcs are happening. Yeah, so it's going to be interesting to compare what maybe similarities and differences. In terms of electron temperature mentioned, yeah, the electron temperature can be high before, so there can already be some significant heat flux coming from the magnetosphere, even without SAID forming at that time. So this can be the combination of frictional heating, heat flux, and also transport from lower down. Yeah, so probably it's misleading to just look at electron heating and discuss Steve. There are lots of things going on. So that's why we want to work with Matt and other people to understand what's going on in the vertical direction.
Thanks, Toshi.
Thank you.
Thanks. Very nice talk.
Thanks.
Bill Archer wanted to ask a question. I saw a hand, that's why I was confused.
I just made the comment very briefly in chat that Swarm has its own problems measuring ion temperatures, many problems, but any set events I've looked at 500 kilometers with Swarm are very, very hot. They are everything's saturating. So,
Bill, would you be able to tell? I mean, this is a thermal temperature measurement. So what does it look like when you have just like a hot tail on the distribution? Does that come off as an average energy?
So we're looking at sort of velocity space of the distribution, and the best we get is the second moment of the distribution. So we would miss the tail with the sort of observations we get.
I see. Okay.
I have one more question for Toshi, if that's okay.
Sure, yeah.
Yeah, that ring current model you showed, was the only difference between the two cases where the injection happened? Or is there
Yeah,
other
the
differences?
strength of the injection is exactly the same. So if you see it at a measure of entropy, so it's on about the same entropy, same depth of entropy, the same width in local time, same duration. But no, the resulting ion and electron distributions in the inner magnetic sphere are very different because of the magnetic drifts. So that drastically changes the electric field configuration in the inner magnetic sphere, because we see lots of electrons over the meridian of Steve. So it's real key how to bring these electrons over here. That's not really happening for normal substorm injections, but for some special ones when Steve is happening, it appears that we have to bring these electrons here, and the way we can do is to inject plasma in this local time, so the electrons can directly access. So the boundaries were doing some strange things where connection has to happen over here. Well, that one by itself is a challenge. We still don't know why that is happening. But if that can happen, then we can explain why the SAID can happen in this region.
I was going to ask the same, what was the magnetotal configuration and where was the reconnection region to have those injections? And I also have a question. I might be wrong, but if I remember correctly, the late studies by Joachim Björn in the 90s and also the early studies of the Themis mission by Christine Gabriels in the late 2000s show that most injections occur in the pre-midnight sector. How far away is that? Because if that's comparable to what you're observing, then I wonder why we don't observe SAIDs more often than we do.
So yeah, and the injection is not centered at midnight, and it's probably 23-hour local time normally. But this is 21-hour local time. So we have also done the bubble injection at 23-hour local time. It didn't change the picture too much because these electrons are not coming to this sector anyway. So only when we shift the bubble really far enough from midnight, then we start to see the drastic changes from SAPS type to SAID. Yeah, it is indeed a question why this is happening. So we know that injection can happen far away from midnight. There have been lots of Themis measurements to confirm that. But like you have done in your earlier paper, there's nothing special going on in the solar wind. So it's not like very strong BY or strong dynamic pressure. So it's just a normal disturbed condition. But somehow, the injection region is shifting, and Joachim Björn and other people have done such simulations, but we still don't know in a fully self-consistent manner what upstream driving conditions can determine these injection situations.
Thanks, Toshi. Carlos.
Just quickly related to this, you're seeing or you're looking for differences in the suborbital region. So I'm guessing that by shifting this from midnight to the sunset, there are consequences in other regions like Aurora or some other places. So what kind of signatures would you expect that could be going along this change from SAPs to SAIDs at different latitudes?
Well, in the auroral zone, the difference we expect is this. So this was stuff I brought up yesterday, but by bringing injections at 21-hour local time, the maximum auroral intensity happens over this side. So the lower maximum is not at 23 or 24-hour local time anymore. So we dump strong heating over here. And so that's the area where Steve is happening. And that's really different from normal substorms where the peak is happening around 23-hour local time. So there are lots of ions getting transported to pre-midnight, and that's a classical understanding of why SAPs, proton, or trough that are forming. In this case, protons are going far away to an earlier local time, but also electrons are still hanging around in this area. So that's a major difference. Also, the neutral wind pattern is different. So yeah, Junlian has studied this. So stronger neutral wind is blowing in this area. That's simply because there's stronger Joule heating, particle heating going on over here. So yeah, those are the major differences we know so far.
Okay, thank you.
Thank you.
Thank you, Toshi. This was fantastic. So we're going to switch gears a little bit right now. We're going to talk to the modelers, and they are going to tell us what are the model capabilities that they have and the model results that they have obtained for Steve or for SAPs or for SAIDs. And we're going to start with Brian Harding.
Do you want me to share the screen, Brian, or do you want to go ahead and?
I can go ahead and share my screen here. If I can find it, here we go. Okay, so first off, thanks for the conveners. This has been an excellent conference so far. I want to talk a little bit about the emission chemistry, and I was put in this modeling section. I think it's a bit generous to even call what I did a model, but let's go on with that. Okay, so just a quick background. Here I'm interested mostly in this continuum emission, which after the Gillies spectrum was sort of, in my mind, one of the major unanswered questions of Steve. 95% of this brightness is from this continuum emission. This is the data from the Gillies paper. And I think it's safe to say we still don't know what this is, but what I thought I'd do is start with something we know, which is that this NO2 emission is known to produce continuum. This is a picture actually from the shuttle, and they had a bunch of investigation in the 80s and 90s to figure out why there's this glow on the surface of the space shuttle. This is the surface that's ramming into the neutral atmosphere at 7 kilometers per second. So through some, we discussed this a bit yesterday, Josh mentioned this, through its, I don't know if it was accidental release or a serendipitous release of NO, determined that this brightness is most likely the NO2 emission, but it raised the next question of where all the NO came from to make this emission, and that's still unanswered. So there could be an interesting analogy here. So let me just jump to my hypothesis real quick. This was already mentioned, so I'll go through it kind of quickly. We know that this process can create continuum emission. So where does all the NO come from? Well, the NO could come from what we propose, vibrationally enhanced nitrogen, very highly vibrationally enhanced nitrogen, the 11th quantum level. And once you get to this level, it's the activation energy of this reaction, which can convert largely nitrogen and oxygen atmosphere into NO and N. We think this could be related to just regular old billiard ball collisions with fast ions hitting the N2 atmosphere. And so we developed this quote model, but it's basically just a super simple finite difference time domain simulation where it tracks some neutral species and ion species, some selected chemical reactions and emissions, including this NO2 emission. But it's I don't have any transport in here, no energetics, everything's steady state except for the chemistry. So this is really just a toy model. It's on GitHub if you want to play around with it. But the punchline is if you take an MSIS and IRI atmosphere, create SAID-like conditions for 100 seconds or so, and then turn on your vibrational nitrogen, you can get an emission that reaches about 1,000 Rayleighs in this model. Another very important part and a confusing part of this NO2 emission is that it has to go away. I mean, the continuum emission for NO2 is not only confusing for how bright it is, it's confusing that it goes away almost immediately too, because the lifetime of NO normally is hours to days. It's one of the ways the thermosphere cools itself down. So it has to go away quickly too, and that is almost entirely determined by the atomic nitrogen density here. So this reaction happens, but then it happens in reverse almost immediately, but not before some continuum emission can be created. So the punchline is this worked in this toy simulation, but there are some problems with it. And I think if I had to pick one thing that we need to model next, it's taking some of these fancy models that track dynamics and energetics and non-MHD situations, and adding a dynamic neutral atmosphere to it, at least maybe some extra vibrational states of nitrogen or some of the chemistry that we've been talking about here. And on the observational side, I think it's really important to put forward ways that this hypothesis could be ruled out. And one of those ways is more of these observations of the Bill Archer type, where we have co-located measurements of velocities from spacecraft overflights and optical emissions confirming that Steve was there, probably from citizen scientists. This thing only works if the ions are going about 4.4 kilometers per second. It's a pretty sharp cutoff. And so if there's a number of observations that are nearly co-located that come in at 2 kilometers per second, but there's a bright Steve there, then I think this is wrong. Just one more quick slide, because Phil and others had put this forward with a lot of confidence yesterday, so I wanted to point out all of the things that don't make sense about this hypothesis. One is that I don't think we really understand the vibrational nitrogen excitation well enough. It was very rudimentarily handled in the paper. And so I think we need a better kinetic model of that. I mentioned this thing about the emission doesn't decay to zero. That's a problem because we see Steve, but then we see it go away. It doesn't really leave a ghost behind. So that's something that needs to be handled. You can see here, it does go down, but not to zero. One is the spectral shape. I think we really need more observations of the spectral shape. The Gillies spectrum was just astounding. And I know there's been a few more, but I think there's some work that needs to be done comparing it to the NO2 spectrum to see if it really makes sense, because the first glance, it doesn't match quite right, but that could be because a number of vibrational rotational states that go into the reaction. So that needs a close look. One thing that happened since I wrote this paper a whole pandemic ago was that there's been some more reports of Steve at higher altitude. And I think that's going to be very important, because this just doesn't work if it's up at 200 kilometers, I don't think. So is that just the red line that's up there, or is it the continuum? I think we need a lot more triangulated observations. And of course, it would be nice for any theory of Steve to be unifying. This vibrational nitrogen really doesn't explain the picket fence at all. But one thing that might do that is actually electronically excited N2, the N2A state, could also create this NO emission. So if you put N2A here, that might explain the continuum and the picket fence, because N2A is one of the sources of green line in regular aurora. So I think I'll just stop there. I probably talked too long. Thanks.
This is great. Thanks, Brian. Questions for Brian? Carlos.
So I guess you are starting to think about a mechanism or some kind of modification that will allow you to have these emissions happening above 200 kilometers. Would that be simple?
For the continuum emission, I have no idea. For the red line emission, I think there's a number of options. Yeah, unless you get transport very quickly up to 200, but it's a problem.
Okay, thanks.
Phil.
Just very briefly, Brian, because now I'm going to be even more circumspect when I describe this result. No, I like your points; they're excellent. But this 4.4 kilometer threshold, I mean, that's going to be a pretty hard cutoff, right? I mean, just because of the energy levels required. Is that what you're referring to here?
I think so. Yeah, there's some blurriness in that because of if there's a high ion temperature, right? But it's fairly sharp because you need to have enough energy to excite to this 11th vibrational level. And if you look at the curve of the reaction rate of this emission as a function of vibrational level, it's really sharp at V of 10 or 11.
Okay, so that answers my last question, which, right, could you have a slightly lower but still pretty extreme vibrational state, like not the 11 and still happen, but so it's really sharp, huh? You've really got to kick it up pretty far.
Yeah, turn it up to 11.
Oh, thanks.
More questions for Brian.
Brian, yesterday you were talking about, I'm trying to remember, you were talking about how there might be some measurements of timing available in the optical emissions that would support or disprove this. Where I don't see any time constants connected with.
Yeah, this was another slide I was going to give, but we talked about it yesterday, so I didn't. Yeah. But I don't know if that will necessarily disprove this, but I think it's really promising. If you look, so okay, the time constant, just to cut to the chase, in the model, in my model, was about 3 to 7 seconds where the NO2 was bright. Largely, that's just look at the atomic nitrogen density. If you work out 3 to 7 seconds for a 5 kilometer per second flow, that's exactly the width of the picket fences reported by Bill.
Mm-hmm.
Okay, so okay. I think if you see a bright emission from NO2, that could go away quickly because that implies high N. But if you see a dim emission with sharp features, I don't think that works with this mechanism.
Okay, I got it. Yeah. Thanks.
Yeah.
The shortest is the steep with the shortest time scale is 1.5 minutes in this Canada Thanksgiving the night. The night storm, somebody observed that as steep, but it's very short, short-lived, only 1.5 minutes. So. And also, Brian, also you missed one other possibility is the collision between the nitrogen 2 and the fast atom. The energetic atom, the atom and the oxygen atom. Or even with O1D, which is the source of the red line. They have enough energy to overcome the energy barrier as well.
You mean O plus N2?
No, like neutral atom, fast neutral atom. Or even the O1D. O1D has the enough energy, almost enough energy to overcome the barrier. O1D. O1D is the source of the red line.
So O1D plus
O1 is close to 3 eV. It itself has this energy of the 3 eV, and it's only I think it needs a vibration level of about 4 to overcome the energy barrier. That's one possibility. The other possibility is the collision between the nitrogen 2 with the fast atom, neutral atom.
It's what I typed in the chat. Was that the reaction you're proposing?
Oh, sorry?
I typed in the chat just to make sure I understand your point. Was that the reaction that you're proposing?
Yeah.
Yeah,
that's just possibility. I agree. There's some problem with that. There's all sort of the continuum, the scenario. But I just mentioned some kind of additional possibilities.
Yeah, I think so. I think there's a lot of stuff at these few EV level that we need to look into. It really changes the chemistry when you have those. And Evgeny made the point. There's a lot of super thermal electrons here.
And the other thing is, during the pandemic, I just stayed home and I work out some sort of the translational cross section between the N2 and the oxygen, the translational cross section. Some work out before. I don't think you have that cross section in your model, but I just work out some kind of the theoretical form of that the cross section, but limited to only translational.
That's great. I started to do that and didn't get far enough. So let's
the translational between the NO plus and N2. The translational, the cross section.
Yeah, I know what you're referring to. Yeah, let's work together on that. I mean, that was the missing piece, and that was one of the missing pieces in my paper. So absolutely.
I was going to ask June if you want to show something later today, if you want to.
Yeah, sure. I can show something that today. But
That sounds awesome.
yeah. So if you have time, I can show something about this the Canada this Canada Thanksgiving storm. Something really strange, some weird.
Thank you, June.
Yeah,
be great.
Thank you, Brian.
Okay. Thanks.
So next we have, who's next?
Matt, I think.
Matt. Matt, are you ready?
All right, I'm on a different computer now. Okay. Hopefully the audio is a little better.
It's much better, Matt. Thanks. It was repeating your words several times, and it's much better now.
But you have the same hat.
I have the same hat.
Yeah, you didn't change it.
I didn't change the hat. My undergraduate institution, University of Memphis. All right, let's see. What I want to do is share. Just bear with me for a second. I'm trying to shuffle stuff around. All right. Are you looking at a slide?
Looks perfect.
Okay, cool. Now, if I can just make this. Oh, well, I don't need to see my own slide. So I know most of you all. I'm Matt Zettergren, and I wanted to talk a little bit about mostly about modeling capabilities and some preliminary attempts that we've made to look at the plasma environment for SED or possibly Steve. And so it's a very different perspective than what Brian just talked about, because it's the charged particle part of this. So I don't have a complicated neutral chemistry model as part of this. The neutral atmosphere is more or less assumed, and we're looking at the dynamics of the plasma. And I've been working, I am in many regards not qualified to give a Steve talk. I'm an ionospheric modeler. My expertise is ionospheric plasma physics, but I've actually not worked in this area at all until about 4 weeks ago, when I realized that I was asked to give a speak at this and show some modeling results. And so I started talking to Toshi and Josh about this, and we kind of threw together some notional simulations, and they're very preliminary. None of this is publication quality. This is just stuff that we're trying and thinking about and throwing out there. So please don't misunderstand this. I am going to engage in possibly even wild speculation here. But anyway, one thing that occurred to us as being important that had not been explored super carefully was the issue of energetic electrons, which, as Toshi showed, there aren't many, but you are on the edge of a conductance gradient, as he mentioned several times, and then possible instability effects as well. So I wanted to talk a little bit about the plasma model. The ionosphere is a fairly complicated plasma in the sense that it's collisional, it's transport matters, chemistry matters, transport of both the diffusive and convective nature matters. And so there's really a lot going on and a lot that could be happening. So this is our ionospheric model. It's a local scale ionospheric model, Gemini. And what we're basically trying to do with this, or what we've been trying to do with this, is model the region around the Steve. And I'm really calling this I think this is more properly called a SED, because I haven't necessarily plugged in the most extreme conditions that we're seeing, for reasons you will understand shortly. But anyway, we do track separate species, but I need to qualify this. These are ion species. I don't track the evolution of neutral species self-consistently. That's actually provided by the MSIS empirical background atmosphere. That's where we get our atmospheric information, and then winds are provided by HWM14. I've turned off winds for these simulations, and I would also note we've had some problems with MSIS 2.0. We're talking to NRL about this right now, so I've actually not used that either. I'm just using the older version of MSIS. But anyway, a way of thinking of this simulation, it's a local box, a three-dimensional volume, and you're putting energy sources in the top of it, and that can be particle precipitation. it can be flow fields or electric fields, it can be current density. And then you have, you have initial plasma conditions and neutral winds and densities if you want to add perturbations. For example, you could add, if you have a specification for a gravity wave field, you could add that in. I don't know if that's at all important here. I don't want to presume that it is or isn't at this point. So anyway, for purposes of doing SED, particle precipitation and boundary electromagnetic fields are what we're using. And I kind of base these off of some work that Toshi and Josh have done. Our code's on GitHub. It's fairly well maintained. We do periodic releases. It's a fairly complicated model, but if you're interested in using it, I can help you get set up. We've got a number of groups at Dartmouth BU, and we had a REU student over the summer at Haystack that used the model. So it is possible to learn it. It can be run on a laptop, but we're typically running this on large workstations or HPCs. Okay, and then it gives you, the output is current densities, magnetic deflections, species emissions for superthermal, for emissions generated by superthermal electron impacts. So we don't have the type of stuff that Brian was talking about before. Okay. So this is just kind of a demonstration of some of the stuff that we do. There is self-consistent electrodynamics in this model. We have either electrostatic descriptions that are available, or you can include ion inertia as well. That turns out to be a tricky bit, but I'll revisit that in a minute because it may matter in some situations. So anyway, on the left, what you're looking at is this is like a pair view rendering that one of the Dartmouth students did that just shows current density and equipotential contours and density isosurfaces. It's kind of I don't know, it's my favorite Gemini picture so far. I haven't been able to make any compelling graphics, but this Jules Van Ursel, the student at Dartmouth that did this, put this together with ParaView. And then on the right, the other thing that we can model, because we have self-consistent electrodynamics, not only can we model the typical auroral situation on the left, and I'll play that, you can kind of see, you can zoom around in the model and look at it. You can also simulate various types of instabilities. So I've got 3 of the more common ones: gradient drift, Kelvin-Helmholtz, and then Rayleigh-Taylor instability. So these are plasma instabilities that are known to play important roles in various parts of the ionosphere. So I just wanted to mention capabilities. The last thing I'll talk about, we've used this model heavily to look at gravity wave interactions with the ionosphere, gravity and acoustic waves. And so this is an example of dynamo currents that are generated by waves impacting the ionosphere. And these are waves generated by a convective thunderstorm. And you can just get a picture for some of the filamentary field-aligned currents. You can see some of the ducted wave structure and so on and so forth. So this is probably maybe not relevant to Steve, but I just wanted to mention it as a capability in case it's of interest to anyone. So that Gemini is the tool we're using. I'll talk a little bit about some of the stuff that we've done. Like I said, this was motivated by a paper that Toshi wrote in 2020, which provided some DMSP observations for a number of different events. And what I tried to do is kind of summarize those all into sort of an average SED/Steve-like event. And I don't think I succeeded entirely, as you'll see in a minute, but that was the idea. And the green region here, so I'm sort of modeling the dust toward midnight sector. And the information that I'm taking from Toshi's observations are occurrence, fields, particle precipitation. Our HPC is down at the university right now for repairs. And so I ran these on a desktop and the resolution is not good. And if we want to, if we want to publish anything related to this, we need to run these at higher resolution. Nevertheless, let's look at them anyway. Okay. Oh, Toshi showed this before. And yeah, I was mainly pointing out there is a hint of temperature increase, which we will see in a minute. The current density I am modeling is an up-down current pair of approximately a microamp per square meter. I am not attempting to capture all of the myriad structures that you see here. That's just for a first attempt, that's not going to be helpful. it's going to be too complicated. Half degree channel width, I think that actually might be too large. So here's an interesting one, and I'll come to this in a minute. Very little electron precipitation. You can see, as Toshi was talking about, you're right on the edge of the auroral zone. There's not a lot going on there. What I'm finding is that even a tiny amount of precipitation, like almost at the level of the sensitivity of the instrument, can matter for this situation. So anyway, those are specified inputs, and then stuff we can compare against. We can look at the formation of density troughs. We can look at the formation of regions of ion heating. We can look at electron heating. And ion heating comes with all of the caveats that's why I was asking Toshi about that. He mentioned there are a lot of caveats interpreting this data. So these are slices. It's a three-dimensional model, so I'm just slicing it in 3 different planes. So this is latitude, altitude, longitude, and longitude, altitude. What I have is a thin channel in latitude. I've turned the model on. I've allowed it to evolve for, I believe, 6 or 7 minutes here, just to see how it behaves. And you do see that a depletion forms, and it does convect westward. So you get this structure here. You also have a gradient in the overall background density and longitude, because this is a very extended channel. It's going from, just past dusk all the way almost toward midnight. An interesting thing about the depletion, you can't really see the E region very well, but this is depleted both in the E and F region and quite a bit into the top side as well. There's a lot of heating associated with this, and it blows off a good bit of the ionosphere when it does that. And that is what you're seeing at the bottom here. This is temperature, and I apologize for the smallness of these fonts. I didn't have time to.
Can I interrupt you very briefly?
Yeah,
I know
please.
Heating and one is density, but I don't know which one is which. Sorry, I got lost there.
Yeah. This is density on the top row.
Okay.
And this is temperature on the bottom row.
Perfect.
Yeah, sorry about that.
Thank you.
I could have spaced these out a little bit better. So yes, the blue region you see here are the density depletions that are characteristic of the SED and sieve and subaraural trough more generally. So if you look at the temperature there, it's extremely high. In this case, it is 16,000 Kelvin max. I don't know if I believe that, and in fact, it gets much worse in a second, as I'm going to show you now. I took the same simulation and I ran it for 3 different background fluxes. Okay, so Toshi was telling me at most this was 0.02 milliwatts per square meter for the energetic electron flux. So that was my first attempt, but I also ran it for 0.04 and 0.06 just to see how it affects things. And you can see, starting from top to bottom, density, ion temperature, electron temperature, and eastward velocity here. Dialing down the flux makes the response more severe. And the reason that's happening is because we're treating the magnetosphere as a constant current source. So if you dial down the electron flux, you're reducing the conductivity, and you need a higher potential to push the current through. Higher potential difference means stronger electric field, means stronger westward drift is part of this. So what that tells me is that regardless of whether the magnetosphere actually is a constant current source, it's still the case that the precipitation makes a big difference here. These are probably almost indistinguishable, 0.02, 0.04, 0.06 from an instrument perspective. I don't know if you could even tell those apart. Someone who knows DMSP better could comment on that. So anyway, these are just cuts at an altitude of about 500 kilometers, showing our attempts to model things. This idea should be credited probably to Josh Simiter, but I've also heard other people talk about this, like JP St. Maurice. And this has come up in other contexts, like some of my work I've done with Gareth's group. But anyway, if you do assume that the SED or the Steve is a fixed current source, you get a sort of a positive feedback loop. Okay, you've got a constant current source, you create ion neutral friction, you heat the plasma, you deplete both the F region and the E region. The F region is depleted through recombination. When you heat the plasma, it recombines faster. The E region through the geometry here of electrons leaving up and ions leaving across the field lines. So you're actually just sucking all of the plasma out of this region rather quickly, but you're still forcing a constant current into it. And so what has to happen is, to maintain that constant current, you don't have as many charge carriers, they have to move faster. And so that's kind of the positive feedback loop. They move faster, they heat themselves even more and deplete themselves further, and so on and so forth. So this is something Josh and I have talked about, and it is manifest in the simulation. So these are the 3 runs. Whoops. And this is ion temperature versus altitude and time for 0.02, 0.04, 0.06 milliwatts per square meter. And what you see here is the responses are quite extreme to the point of thermal runaway for the 0.02 milliwatts per square meter situation. The temperature gets so high in the model that it actually crashes the code after a while. I think the temperature is above 50,000 Kelvin at the end here, which again may not be believable, but this investigation was sort of looking at what might be possible from a theoretical point of view, and not necessarily what might be observationally defensible. Okay, so the last thing I'll talk about just really quickly is what caught my eye with some of the measurements Toshi showed is the boundary layer between the strong Steve drift and the surrounding region is extraordinarily thin. There's a really, really strong plasma velocity shear, and that made me think of shear instabilities like Kelvin-Helmholtz here. And so what I did is I went through the linear theory for Kelvin-Helmholtz instability in a inertial ionosphere and just looked at some of the information from the data. So the boundary layer scale, as far as I can tell from DMSP, 10 to 20 kilometers. The density profile is a 3-to-1 change from outside the Steve to inside the Steve. It's 3 times more dense outside, roughly. The shear delta V is about 4 kilometers per second for one of the events that Toshi sent me. And so if you just run that through the linear theory, it's that you will get 100 kilometer vortices, sort of linear. Vortices aren't linear structures. The initial growth is, though, and it'll be at about 100 kilometer wavelength. And the e-folding time is about 60 seconds. So it seems to me that you could have a shear instability to the extent that the shear is maintained by the magnetosphere over, 4 or 5 e-folding times so that the perturbations have time to grow into something. So a lot of caveats. This is a poorly conducting ionosphere type of formulation. That's probably true for Steve for reasons we talked about. And we're also making some assumptions about the boundary layer width. And that is, these shear instabilities are extremely sensitive to how you set that shear layer. So I'll just play this really quickly. This is showing on the left density in the F region, and versus X and Y are just the lateral directions, latitude and longitude. I guess Y would be longitude here, X would be latitude, and then I have ion temperature over there, and you can see it's above 20,000 Kelvin. But if you play it, you can see the evolution of both sides of the shear layer. Now, one of the other heroic assumptions that goes into this is you have to make some assumption about what the magnetospheric inertia is. What is the effective capacitance of the magnetosphere? I put in a number, 5 farads. It's probably too large. And so the actual feature is probably more stable than this. But again, these are, like I said, wild speculation. I'm playing around with the model here and hoping, it generates some useful conversation. So that's it. I think there are a lot of things to do. I don't want to talk too long. I apologize for going on so long. I do want to mention that Christina Lynch has played around with the model, and she thinks that you could actually be tearing mode unstable in some of the Steve configurations. So there's another, KHI is nice because it produces band limited structures. And sometimes you see the folds in the Steve and you think, man, maybe that's a shear instability, at least trying to develop there. She is thinking that tearing mode could be responsible for some of the picket fences. It can produce band limited structures as well. We haven't finished validating that, but she wanted me to mention that. And I wanted to credit her with that idea. Yeah, and then from we've been looking at the citizen science, man, the images and the movies, and I don't know, it's just so awesome. And I started thinking about, all right, what is what can be obtained from that? And I started thinking about, okay, if you wanted to test the stability of the plasma, you can get time scales, you can get wavelengths from sequences of images, you can get group and phase speeds maybe. And so last night was really wonderful because it got me thinking about, the ways in which those data could, take some of this speculation from possibly pure fantasy into, let's test some of these ideas using some of the imagery. So that's it. And I apologize for taking so long, but I also really appreciate the opportunity to speak. This is a really awesome community. I've enjoyed the format of this workshop a lot.
Thank you, Matt. This is exactly what we wanted. Like, what happened if you crank everything up and will your model explode or something? Brian, you have a question.
Yeah, great talk, Matt. I learned a lot. Could you remind me how you handled the electron distribution? Is it Maxwellian or?
Yeah, so effectively, there's a division into two populations. So there's the thermal ionospheric plasma, which we do assume is Maxwellian. And that's actually a problem at these drift speeds. The theory suggests it's quite anisotropic and possibly even not describable by Maxwellian. So if Lindsay's here, she can comment on that. So that's one limitation. The superthermal population is handled through GLOW. So this is like a two-stream Boltzmann code that does impact ionization and inelastic collisions. So this 0.02 milliwatts per square meter superthermal population is being fed through GLOW, and GLOW gives me ionization and heating rates for the thermal population, which itself may have non-thermal features, but we're not modeling that. So does that kind of...
Yeah, I had no idea GLOW was involved. That's actually really exciting because that means that you have vibrational excitation and excited neutral species in there.
Yeah, so I am not, the GLOW integration for Gemini was done by Michael Hirsch, and I know it has all of the electronic states in it. I know you can access them, but to be perfectly honest, it's sort of waiting for the right student / postdoc / scientist / whoever wants to like dive in and make heads or tails of that. Like for me, I was kind of looking at it. I need ionization and heating rates to get the plasma dynamics right. But you're right. There's a whole host of other information. Like if you wanted to tack on a more complicated model of the electronic excitation, you have some of the information there. I think that would be needed.
One quick follow-up from your Maxwellian population. Do you take any of those and drive those electrons through GLOW, or is it only the initial precipitating particles that go through GLOW?
I don't feed back into GLOW, but yeah, you're right. Like it drifts of 4, 5, 6 kilometers per second and temperatures of 10,000 Kelvin. I mean, these things are more than a couple of EV, I think. So
that's where all the action. I think the couple EV is where all the action is at here. So
yeah, so I can certainly generate that, if not just through the drifts, then through the high temperatures that you get. But again, I'm nervous about that. I mean, that's, if you try to publish an article or write a proposal with a 20,000 Kelvin temperature, it's, guaranteed rejection probably. Yeah. But anyway, yeah, looking at Toshi's data, that was the source of my question. Well, how confident are we that there isn't a lot of heating? And could this just be, a bunch of molecular stuff that's been blown up into the topside ionosphere? Because that does happen here. I didn't show that, but a lot of molecular plasma is being moved above 500 kilometers, which is really kind of bizarre, but that's what is happening in the model.
Like on that topic specifically, I want to encourage you not to apologize for any large values, because if you like on the measurement talks that we've had, almost all of a significant amount of the measurements include the caveat, now we checked all of the flags and as best as we can tell, the instrument is actually working, but this is the largest number that we've read off of it. So, I mean, everything agrees that the numbers are big. And I think most of these instruments weren't necessarily designed to measure values as large as they are, but as best as we can tell, like I said, as best we can tell, they're still working.
Yeah, that's part of my question to Toshi, why I was asking him about the high temperatures. And yeah, I think, an important point is what Josh and Phil and Brian have brought up was shouldn't have any preconceived notion as to what this is supposed to look like. I mean, I've never seen 20,000 Kelvin, thermal plasma temperatures in the ionosphere, but these are not normal situations. You also don't get 6 km/s drifts that much either in such a narrow boundary layer like that. So yeah, I mean, I think, there could be a lot of stuff that's on the table here that normally wouldn't be. The other thing is what Brian talked about. You're accelerating the thermal ionospheric electrons above several eV potentially. And so, that doesn't get fed back into the kinetic model, but in principle, it could or should be in some way.
I think Phil had a question.
Yeah, very briefly. Yeah, don't apologize. This is really excellent. This is the only way we're going to learn this is by starting somewhere. So the question was, I just trying to remember from the work that Jean-Pierre and Josh and other people have done in this situation where, the conductivity keeps dropping because you're feeding current into it, right? And where is the limiter? I mean, your temperature blew up, but was this anomalous resistivity that starts to show up from irregularities? Or what is the thing that's supposed to limit this thing from just, or is it just now we're just completely kinetic? Temperatures don't mean anything anymore, and we have to do the full distribution. I'm just trying to understand if there's a physical self-limiting process here that maybe the simulation isn't getting right, but that we should sort of think about.
Yeah, Josh and I talked about this a little bit because, when you look at the pictures of Steve, it does seem to settle into some sort of approximately laminar looking state after a while. You get the folds coming through, and maybe that's a shear instability or tearing mode. But I don't know the answer to that. I know that we don't have the E region turbulence in here. That needs to be parameterized and included because it's a source of electron energy as well. And to the extent we don't model that, we're not getting the electron temperature right. And because the field lines conduct heat so well, that means you're not getting electron temperature right at higher altitudes either. So that's definitely an issue. Limiting stuff, you have photoionization by starlight, you have whatever drizzle is coming in from the magnetosphere. As Toshi showed us, it's not very much, but that's what stabilizes this positive feedback is this precipitation. By dialing it up, you get a more and more, stable situation. Whereas here, for the 0.02 situation, after 10 minutes, the temperature goes above 100,000 Kelvin in it.
Yeah, right. Your floor is just not high enough to do that. Okay, so this is frankly like oscillators in radios. Eventually the positive feedback has to be clamped by something, and usually it's some resistance somewhere that limits it. So what you're maybe just saying is that floor that you just quoted is the place that it limits, and maybe we just don't have the constants dialed right to get that stable limit right. But at some point it's got to stop.
Yeah, another important point here is that there's a generator side of this, like Toshi was talking about. There's the structures out in the magnetosphere that are sourcing this, and I think about these things like transmission lines. Like the generator sends a certain amount of current, the load reflects some of it back, says no thank you, I'm not taking all of that because I'm not impedance matched or whatever. And so like I think over a 30-minute time scale, there's plenty of communication back and forth between generator and load, I would think. So that's another thing. It could be that these currents, the 1 microamp per square meter is just transient. It gets partially reflected back out eventually. I don't know.
Yeah, that's a really good analogy, and maybe one that I could think of some. You're talking about toy models, maybe in the future, some kind of reformulation in that, because there's so much experience with, standing wave ratios and all that other stuff that maybe looking at it in that with that pair of eyes would tell you something more here. I agree with you. There's plenty of Alfvén bounce times in 30 minutes, no problem.
Yeah, all right. What kind of viswar gets negotiated between the ionosphere and magnetosphere here?
Right. Fascinating.
Bill. Was just a comment. Do you have an extra question, or is just the all hand? You're muted. Okay. Any more questions from anyone else? Thank you so much, Matt. This was excellent. And our next speaker is Naomi Maruyama. Naomi, are you ready?
Yes, I'm ready. I was thinking that Tomoko will talk, but I can talk.
Whatever you guys prefer. If Tomoko wants to go first, we can.
No, it's okay.
Okay.
I can talk. Let me share my screen. Oh, okay. I have to share my screen first. Sorry about that. Can you see my screen? Sorry.
We're seeing your desktop.
Okay, and then I have to share my presentation, right? How about this?
That looks perfect.
Okay, that's good. Okay, yes, so, yes, that was a great presentation. My name is Naomi Maruyama from University of Colorado. I don't know if, I think I know most of you in the audience, and can you hear my voice okay? My voice is very small usually.
Perfect.
Okay.
Sound
okay.
great.
Thank you. So yeah, thank you very much for inviting me to this exciting Steve workshop. And in particular, I enjoy the interaction format by connecting professionals and citizen scientists together and creating very lively discussions. And today I'm going to talk about Steve from global modeling perspective. And I understand that Steve is a relatively mesoscale phenomenon. So it seems contradictory to talk about mesoscale phenomena such as Steve from global modeling perspective. So, but anyway, but the main takeaway of my talk is that Steve is an excellent example of mesoscale manifestation of the global coupled magnetosphere, ionosphere, thermosphere, MIT system. And what I'm going to talk about is what do we need to describe and model Steve. And we heard a lot of discussions yesterday and today. And based on that, I made a list of ingredients as follows. So first, substorm injections, and number 2, SAID or polarization jet, and ingredients number 3, heat flux, and number 4, elevated plasma temperatures, as shown by previous speaker. And then number 5, enhanced singlet oxygen atom O1D, and ingredients number 6, NO2 continuum, also shown by Brian previously. And then finally, at the end of my talk, I'm going to summarize and I'm going to show what's next. And I'm going to discuss how each process contributes to the magnetosphere, ionosphere, thermosphere coupling in the Steve suboral science. So actually, I have to let you know that I was not going to reproduce Steve. I haven't made yet. Okay, so ingredients number 1, substorm injection and SAID. And Toshi nicely set the stage that the substorm bubble injection at 21 MLT sector generated strong SAID by using a ring current model. It's called Rice convection model. Can you see my cursor here?
Yes, we can see it.
Okay, that's good. Yeah, just checking. So the ring current is the key to understanding the SAID and the MIT coupling in the suboral region. And Toshi focused on the electrodynamic coupling in the MIT system, but in my talk, I'm going to focus on the energetic coupling by focusing on the heat flux. Okay, so the ingredients number 3, heat flux. So in order to explain the red glow characteristics of the stable auroral arc, say SAR arcs, we show a lot of observation examples yesterday, and Janet Kozira suggested the heating from the magnetosphere elevates the electron temperature in the topside ionosphere. So what is the heat source from the magnetosphere? So there are 3 suggested heat sources in the magnetosphere. Number 1, heating due to Coulomb collisions between the energetic ring current ions and the thermal plasma in the plasmasphere, because it's in the region between the ring current and the plasmasphere boundary region. And then heating number 2, heating due to the electromagnetic ion cyclotron waves, EMIC waves, due to Landau damping. And then heating number 3 is due to kinetic Alfvén waves. And in order to calculate the ring current heating due to Coulomb collision, Janet's student back then, Mei-Chin Falk, developed a ring current model. And then now it is called comprehensive inner magnetosphere CME model. And CME solves a bounce average Boltzmann equation for distribution functions of ring current, ring current and radiation belt particles. And the heating rate due to Coulomb collision is calculated by combining the ring current and plasma, thermal plasma in the plasmasphere. This is an example of the ring current heating calculated by CME as a function of MLT. And note that this heating rate varies dramatically due to geomagnetic activities. This is an example of how heating rates in the ring current varies from the main phase of the storm and early recovery phase, and then the late recovery phase of a storm. Okay, so ingredients number 4, elevated plasma temperatures. So in order to investigate the response of the ionosphere to this ring current heating, we drive the ionosphere plasmasphere electrodynamics IPE model with the CME ring current heating. So IPE model is a global 3D time-dependent model of the ionosphere and plasmasphere, providing electron and ion densities, electron ion temperatures, and plasma velocities. And the parallel and perpendicular plasma transport is treated separately. And parallel transport is based on the field line interhemispheric plasma flip model. It is well-tested model for more than 30 years, developed originally by Phil Richards. And the semi-ring current heating rate is injected in the IPE, the energy equation in the IPE model. So IPE reproduced the plasma parameters observed by the Millstone-Hill incoherent scatter radar at 500 kilometers for the St. Patrick's Day storm, March 17, 2013 storm. And this is the ring current heating. This is the heat flux at 500 kilometers. And this is electron temperature at 500 kilometers. Ion temperature and electron density. And this is for three, x-axis is time, universal time. This is 17th, this is 18th, and this is 19th. And the diamond shows the Millstone-Hill observation, and solid line, the lines shows the model simulations. And the black line shows no ring current heating, and the yellow line shows the ring current heating, include the simulation, including the ring current heating. And the orange line shows the ring current heating, but the increased by factor of 10 to reproduce the observation. And please note that heat flux, the second panel, and also the electron temperature are better reproduced when we increase the ring current heating by a factor of 10, shown by this orange line, especially after 22 UT of the March 17th. And we will need to further investigate to study by studying other events to understand why we needed such a big factor. Perhaps ring current distribution or the plasmaspheric density may not be, could have been improved to improve the ring current heating variation during this storm. And ingredients, Steve ingredients number 5. So SAID can create the elevated ion temperature and enhanced oxygen, singlet oxygen atom. And Stansazigin showed that the SAID of 2 km/s elevates ion temperature due to frictional heating and consequently leading to the enhancement of the singlet oxygen atom here, which is in the nighttime, suboral ionosphere are excited in the dissociative recombination of O2 plus and NO plus, and in collision with atomic oxygen with the thermal electrons. And this is showing that the brightness is increased in response to the artificially imposed SAID in the model simulation. And then this can be another mechanism to reproduce the SAR arc emission. So ingredients number 6, elevated NO2 continuum is shown by Brian previously. It is a very interesting result showing that the NO2 continuum generated by the elevated plasma temperature can reproduce the purple emission. So so this is the summary slide that I summarized all the ingredients required to describe Steve in the global modeling. And to summarize, substorm injections and SAID or polarization jet and heat flux from the magnetosphere and elevated plasma temperatures and enhanced singlet oxygen atom and NO2 continuum. We need to combine all the ingredients together in one model simulation in order to reproduce the Steve by physics-based modeling. And effort is underway in terms of reproducing the MIT coupling of the SAID. So to reproduce the realistic substorm injections and strong SAID as shown by the Toshi, energetic particle flux observation at geosynchronous orbit is injected at CME boundary at geosynchronous orbit. And furthermore, and then we have to drive IPE with the strong SAID and combined with the heat flux calculated by CME to reproduce the heat flux and frictional heating. And furthermore, electrodynamic coupling and heating and ionization due to the CME precipitation is underway to be included in IPE to complete the magnetosphere, ionosphere, thermosphere coupling related to Steve in the suborbital region. And by including both magnetospheric heat flux and also the SAID frictional heating and also the MIT electrodynamic coupling, we expect to reproduce more realistic emission eventually that can reproduce the Steve in the global modeling. Thank you very much.
Thank you, Naomi. This was awesome. Questions for Naomi? Toshi.
Yeah, thank you, Naomi. I think the inclusion of heat flux is really important in here. So are you able to tell how much of the heating comes from heat flux versus Joule heating in your simulation?
So yeah, we haven't gotten that part yet. And one of the reasons is that in this version, we didn't include the neutrals yet. So yeah, we have to reproduce this with the warm IPE, the coupled atmosphere, neutral atmosphere, and the IPE version. And then we can evaluate the relative importance between the heat flux, heating due to heat flux from the magnetosphere versus the Joule heating due to the ion neutral frictional heating. Yeah, that was a great point. Thank you.
I see. Can you go back to the slide where you talked about the heat flux in comparison to the radar temperature measurement?
Yes.
So in here, yeah, you mentioned you cranked up, during current heating by 10 times, but in some areas, there's almost no difference, for the simulation, with and without the factor of 10 multiplication. So why, the current flux doesn't play a role for certain situations?
So are you talking about why electron temperature didn't increase very much here?
So what I mean is that, so in here, the difference is pretty clear.
Oh, yes.
In here, there is no difference between the two lines. So I'm wondering why the factor of 10 didn't play a role for heating in the ionosphere.
Okay, so this is looking at the Millstone Hill and then, diurnal variation. So during the day, this is during the day. So during the day, the thermal balance is dominated by photoelectron heating.
Oh, got it.
Yes. So that's why it didn't impact very much in the electron temperature or ion temperature either. But then it's only during the nighttime when the density starts to decrease and also the photoelectron starts to decrease, then we can see the impact of the magnetospheric heating. So that's another thing that temperature calculation is determined by the heating balance between the photoelectron heating versus the magnetospheric, whatever the energy is, the heat flux coming from the magnetosphere. So we have a lot of uncertainties, but in this particular case, yes, we needed to increase this magnetospheric ring current heating by a factor of 10. But we really need to do other simulations, other events to see how this uncertainty varies depending on the geographical and geomagnetic conditions.
I will also say, unfortunately, observationally, as Naomi is demonstrating on the page, in the conditions where you really want to make that measurement, the floor is dropping out of the electron density, the temperature is going up, and you can see from the scattering points, the observation gets really, really hard. Because unfortunately, just as you really want to nail that temperature, we're losing the scattering signal. And the other thing, Naomi, is that even though you're probably using our vertical measurements there, if I remember correctly, just the vertical profile, there is structure in the vertical profile too, due to transport. And so that's also mixing in here, and it's a real challenge. I think the only way you're going to do that is what you said, is to try to look at multiple events. Some of them you get lucky and the density won't drop so much, and you might be able to get better data. But Toshi, it's a real challenge in here to get the right thing. And yet, as Naomi said, the heat flux, if you're going to nail it, that's the place you got to look. That's the really critical place.
And also, this is within the SED density enhancement here.
Yep.
So yeah, that's another thing. We have to be able to reproduce the right amount of density so that we can, so the cooling, electron cooling is determined by the number of ion densities. So if it's too much electron density, the density is too high, then the temperature goes down. So it is a lot of nonlinear interaction is going on here. Yeah.
Yeah, thanks for. I wanted to ask that one too. So looks like this is not kind of trough region, and we see even more heating, in here and there. So I guess we need even higher heat flux to explain this.
That's right.
Yeah, I forgot to exactly, Toshi. The boundary is now coming close to us and probably pretty close to overhead too. So you're even crossing into vastly different conditions, and it's probably fluttering back and forth at that point.
Yeah. All right, thank you.
Thank you.
Any more questions for Naomi? Thank you, Naomi. This was very, very interesting. So our next speaker is Tomoko Matsuo. Tomoko, are you ready?
Sure.
I don't think Evgeny is here yet.
Do you hear me?
Yes, we can hear you.
Good. Okay. Good. So hold on. I'm gonna share my screen, which is the same slide as hopefully you all have access to, or I added few stuff here. So I thank you. Hello, everyone. It's good to see you. So I was listening to very interesting talks, and I'm very excited, and I really like this format and structure. And it would have been, great that if you could meet. But this is great. Thank you for organizers, and then thank you for asking us, myself, and then student that you're gonna hear after me, Valerie, to be here. But then I was just wondering why we end up being here. So I just want to say a few words about, because I think because we are talking with Liz McDonald here. So this is a poster that the Valerie Svali presented, first ever AGU presentation she made back then that we can still meet in DC. So you might recognize that we are looking at, or might be how, but we are running one of those these that basically those are 2018 Steve events that featured in this McDonald's paper. But back then, I had no idea what the Steve is actually. Wasn't really much. And then we were interested in sort of reproducing sort of global electrodynamic features that is basically observed by student scientists. So how it started, because we talked to Liz, and then she told us about Steve. And then Valerie made these presentations, and then she made lots of friends at the AGU. And then she met Bear, and then talked to other Steve investigators. So that's how it started. So I'm Tomoko Matsuo, and then I'm at the CU Boulder, and then I'm here to introduce our tools. And then we are sort of bundled together in the physics-based model tools, but it's not quite a physics-based tools. This is a data-driven assimilative models. Okay, and then so Steve is very interesting, right? I mean, it's really like a regional, localized phenomenon in pre-midnight suborbital regions. But because of these connections that we start running AMSGEO, large-scale assimilative mapping procedures for Steve events that observed by student scientists, we start finding that, there might be something going on. So that's what it is. So AMGEO, assimilated mapping of geospace observations, this is a project being funded by NSF ASCUBE program. And then we released this Python-based assimilative mapping software. And then, so this is software that you can download, open source, and then you can run on your own desktop, laptop, and then you can produce these convective maps using default data as a SuperDAN, SuperMag, and then Ampere. Right, so those are the data sets global data sets that you can assimilate. And then if it's, because it's open source, you can add your own data sets on top of it. And then okay. And then so software talk to database. So great thing is that once you start Python session, you never have to leave Python session, because the software talks to SuperDAN, Virginia-Tech database, grab SuperDAN data, and then SuperMag, and then so as Ampere. And then, okay, so it makes lots of things easy. Okay, so so the physics that we have is a super simplified physics, which is, okay, so, but we use sort of linear relationship among all the parameters that we feed into this assimilated mapping. And then it's derived from Richmond Camille. I started out as Camille student back in Japan, which is funny that I end up being here. But anyhow, so those are the state variables that we are solving, and then we have because it's assimilated mappings, we use background models, and then combine with those three major data source, and then create complete maps of, for example, convection maps, and then we could create Joule heatings, we could create conductance, and then aurora energy flux and so forth. Okay, so that's the tool. Okay, so then what we have been doing, because of those connections that actually Valerie Spaldi that you're gonna hear from, she ended up making lots of friends each time she goes to AGU. And then I think she met Bear, and I met Bear through her. When was it? Like 2-3 years ago? And then she said, oh, you should run more Steve events. And then you should run more. Okay, you should look at this study that, so this is you heard from Toshi Nishimura's. And then this is an interesting thing going on. There's those are related to, Steves are related to substorms, but substorm without Steve and then with Steves are different, right? And then also, as everybody's pointing out, that it's a regional, it's suborbital phenomena pre-midnight. But it looks like there's something that other people are looking at, is that it's actually global electrodynamics as represented by convection patterns are different for these two classes of substorm events. So because we automated this assimilated mapping procedures, now we can run many events, which you can do it too. But we did it, Valerie did it. So with various patient encouragement, we end up running 64 substorm events. 32 of them are with Steve, and then with the other 32 basically control events, the substorm without Steve. And then, so this is a convective maps at that substorm onset time. And then we produce this convective map every 5 minutes. Okay, so this is we always call this Toshi events. So 2008 March to 26. So you can see that. Okay, so here you go. Substorm onsets is 6:30. Right. So here you go. So it's here is a substorm onset. That's how convection pattern look like. And then at the 7:20, Steve is observed by Oscar image. And then that is also coincide with the bottom of AL, which goes down to, I think, about minus 830 or something, 830. So this is around the time that Steve was first observed, 7:20. Look at this. So one thing that we really noticed, and then that Valerie could show more, is that this whole penetration, intrusion of the morning cell and into the pre-midnight. And that's amazing sort of intrusion, and then this great sharp gradients or sort of distorted convection patterns, and then really concentrated in the midnight. And then we look at it like many events, and then persistent patterns. And also we looked at the timing and how long this prolonged westward intrusion of morning cell, how long that lasts with respect to substorm phase and so forth. And then Valerie could talk about it. And then we really think that in addition to what Toshi and then others been talking about, that basically sort of you could see it in terms of particles that the dynamics are very different, but global electrodynamic and or convection patterns in a magnetosphere is also very different from substorms associated with Steve and then substorms without Steve. And then so just the caveat is we are focusing on global scale patterns. This is not the tool to really could see that there's the SAID, but maybe we could infer that from this sort of gradients of convection patterns. And then so that's our tools. And that might be useful for example, Naomi's model simulations, boundary conditions. I don't know, she was using, I think she probably needs something at the high latitude to drive that models. And that might be useful for maths, regional modeling. Maybe that's useful to set the boundary conditions. And then we run this many events, and then Valerie can talk about it. And then we can share the data. Okay, Valerie, do you wanna take it?
Yeah, sure.
Gonna stop sharing.
Well, you guys changed slides. This is amazing, Tomoko. I want to advertise to everyone that this is the work that Valerie did as an undergraduate student, which to me is incredibly impressive. So Valerie, it's all yours.
Oh, thank you. Well, I was just about to say, yeah, why am I here? I am a metallurgical material engineer. I just graduated with my bachelor's in that from the Colorado School of Mines. And now I'm a first-year master's student at Mines studying space resources. So, but when I started studying Steve, it was during a research experience for undergrads in 2018 with Tomoko, and I totally fell in love with it. I thought it was just so mysterious, so interesting. And then I got to meet amazing people at AGU like Bea and like Toshi and some of the citizen scientists and Liz. And talking to them just made my excitement grow. So I'm very lucky that I've been able to continue doing research on this. But what I'm going to talk about today is just kind of highlight some of the key aspects and important results we've gotten from our case study looking at 32 Steve and 32 non-Steve, and particularly the high latitude global ionospheric convection patterns that are observed during these events. So we're going to start with a case study where we have a Steve event and a non-Steve substorm event in order to investigate and identify kind of key global convection features that are unique to only Steve. So on the left, we have this Steve event, the Toshi event on March 26, 2008. And we have maps shown from 6 o'clock UT until 9:15 UT. And there's a lot that we can look at in these, but I want to start by highlighting this, this map here at 7:20 UT. And I want to highlight it and point out the morphology of this, what we're calling a dawn cell extension. So basically we can see there's a prominent westward extension of the dawn cell into the pre-midnight sector in the vicinity of subaurora latitudes. And this prominent dawn cell extension feature that we observed is in the majority of Steve events. Out of 32, we saw 27 that had the same or a very similar feature in their convection pattern. For comparison, we have this non-Steve substorm event on September 14th, 2015, from 14 UT to 17 UT. And at 1540, again, highlighted here, we can see the morphology of the dawn cell is weaker and not as far extended into the pre-midnight sector. And this tends to be the typical case for non-Steve substorm cases. And these plots are really useful for our study for looking at the timing and the progression of this dawn cell extension and the evolution of these convection patterns through in terms of substorm phases. So we highlighted some key times here for both categories of events, with the black dotted line that is indicating the Steve or the substorm onset. And then the black solid box for both categories of event is the AL minimum point. So where it's transitioning from the end of the expansion phase into the beginning of the recovery phase for a substorm. And then for Steve events, we also have this pink dotted box showing the Steve optical onset time. So using those 5-minute resolution AM geoconvection maps, like we just saw in the previous slide, for a 3-hour duration for all 32 Steve events that we looked at, we were able to generate these mean convection patterns. And we did this for both all 32 Steve events and all 32 non-Steve substorm events. So these are heavily diluted means, but we can still see some things come out of them. For example, for the Steve event, we see the dawn cell has this slight extension past the midnight boundary into the pre-midnight sector, and that it's got a strong puff polar cap potential of 48.15 kilovolts. When we compare that to the non-Steve substorm, it's a lot weaker, and the cross polar cap potential is 39.32 kilovolts. We then looked at characterizing the global modes of ionospheric convection variability that we see in Steve events and in the non-Steve substorm events. So to do that, we did a principal component analysis, and we have the first 4 principal component spatial distribution maps for both categories of events displayed here, where again, we can see overall the morphology for these 2 categories of events is pretty similar, with the exception of the spatial morphology of PC3. So PC3 for Steve events is very asymmetrical pattern, wherein the dawn cells extended very far westward into and past the pre-midnight sector. Whereas, and this particular principal component is of particular significance to our study because it's a dominant mode that's associated with Steve in the visualization of this westward dawn cell propagation trend that we observed in the Steve events. And then the PC spatial morphology for the non-Steve events, you can tell, is noticeably weaker and has a reduced extension that's actually more centralized around midnight. So just to quickly summarize some of the main differences that we've seen between the Steve events and the non-Steve events in terms of the morphology, magnitude, and timing differences. So for morphology, we've seen a prominent westward extension of the dawn cell in both the AMGO maps and in the PC3 spatial morphology. So both of those have for Steve events have a dawn cell that's found to be typically farther extended into the pre-midnight sector than for non-Steve substorm events. We also have a larger magnitude difference for Steve events, or cross-polar cap potential value for Steve events. And in terms of timing, this significant dawn-dusk asymmetry that we see in Steve tends to last from the growth phase all the way through the recovery phase. Whereas for non-Steve substorm events, it's typically from the growth phase to maybe the end of the expansion phase or very beginning of recovery phase. So it's a little bit shorter of a duration that we see the asymmetry for the non-Steve events. And with that, I will open it up if anyone has any questions for me and Tomoto.
This is excellent. Thank you, Valerie. I see Liz has a question.
Okay, yeah, excellent work, Valerie, and really exciting to see. Similar to what Toshi was showing, how the Steve and the non-Steve times, it goes more towards dusk. So my question is on the Steve events that you looked at, do you see that peak moving around dusk? Like, could you just say that, sometimes it's earlier and sometimes it's closer to midnight, or do you have any? Yeah,
there definitely is variation, I would say, between the events. And so there's some that are farther, I guess, even more pronounced, and some that are slightly less. So yeah, there's definitely variation between event to event.
Okay, great. Thanks.
Yeah, thank you.
One of the interesting things is that although, as you said, the means are very diluted, you still see some of that penetration in the means. Toshi, sorry.
Oh, I think it's interesting too from the PC3 perspective. Again, that's all of the Steve events. So even if it's different from each event to each event, the overall is showing the same trend.
Yeah, Toshi.
Yeah, but then Liz, I think we should be able to look at that. We haven't looked at the extent of this, sort of how far that goes. The PC3 that Valerie is talking about, we could look at it actually by putting magnitude of the PC3 mode. That, well, we probably have to eyeball to some extent, but yeah.
Yeah, it's definitely a strong result, that you see in the statistical sense. And my question was just kind of about individual cases, how much they vary, because I think there's also something more to look at possibly, and which ones are way more duskward and which ones kind of could be closer to midnight and why and all of that. Yeah, thanks.
We have some weird ones too that we could show tomorrow during What Is That section.
Awesome.
Timing is also complicated because since for Steve, the timing is determined by the imager, you could have a Steve event that has leave the imager, but is still there, visible in the west. So timing is always tricky to evaluate too.
That's actually, we grapple with timing. We looked at the AL to classify or categorize, but it's really hard. That it's sort of biased that, because we have all that ground-based observing network that is probably gives sort of, the timing is always biased. Well, yeah.
Yeah, well, I agree with that comment too. There's a pretty dynamic time evolution, so it really matters which time to select to superpose, although it can be played based by looking at OR or something. My question was, I might have asked this to Tomoko some time ago, but do you see anything special in the solar wind that might explain this strange convection feature? Bear and I tried, but we really don't see anything.
Yeah, go ahead, Valerie.
Oh, just very, very small BYBZ values, and nothing that's drastically different between the two subsets of Steve and for non-Steve. There's not a glaring external indice that's pointing towards anything. So it is kind of what's causing this.
Yeah, it's still a big open question.
Yeah.
Another thing I wanted to ask was, for the non-Steve events, could you tell us how those are selected? Are they random events or are they controlled in some ways?
Yeah, actually, so the non-Steve substorm event selection was a big process. Initially, we picked states that were similar in UT time and like season the same month as the 32 Steve events. But then what we did is we actually went back and reselected events that have similar AL values to the Steve events. Because we didn't want to be comparing, on one hand, Steve events substorms tend to be a lot stronger. So we didn't want to compare really weak substorms to those, right, or, exceptionally strong ones. But I think something that would be really interesting in the future to look at is substorms that include SAIDs and SAPs, so that we can look at what the global convection patterns for those look like in comparison to Steve, and if there's any kind of things that we can determine are different between those global patterns.
Yeah, that's a great way to control a data set so that the potential difference you saw is not a significant one. So maybe there's a key in there why the Polarity potential was larger for Steve. I guess that's something we need to know to understand why the convection is so special. Yeah, thank you.
Because it seems like really consistent with what you were saying about the sort of, the prolonged this penetration of morning cell, like really lasts into the recovery phase, and that's what you see what others are saying, and that's really nice to see that it's a mystery. I mean, I know, like my mind rushed that, okay, now we, this is some sort of patterns, but it's great to see that all the data sets kind of like telling that consistent story.
Yeah, and I'm pretty encouraged by it, seeing the convection pattern that you and Barry have shown, because I can only see Aurora. I don't know what the convection pattern is doing, so it's really encouraging to see everything is coming together. So now we need to understand why the flow pattern is so distorted. So yeah, that's a great step forward.
Okay, thank you.
Yeah, this is Phil. I would say that if I describe this result to someone, they would basically say, wait a minute, you have a global result that is actually predictive of something that's really local, and they're going to ask me how to connect the dots. And so that's exactly the kind of connection you'd have to make. I think it's fascinating. Yeah. And I don't think it's going to just be, oh, this is just completely random. There's no way it is. Yeah. But the exact path to get from A to B would be really interesting if we could lay that out.
Yeah. That really excites me, because I've been looking at global things and then like, wow, and you could connect the dots. Maybe not, like I think what you this workshop is really great about is I have to be open-minded, because I want to connect the dots, and like, yeah, was a problem, but it's good cues, I think. Okay.
Terrific. Really nice work.
I guess I would like to ask something related. This is something that Valerie, Tomoko, Liam, and I have been talking for a couple of times, and I would like to hear Toshi's opinion on this. So one thing that we were thinking is that distorted to cell convection pattern could be leading to the formation of a Harang reversal. And there are all papers by Shasha in the late 2000s and Martina Giolidu in the late 2000s, where they talk about the Harang reversal increasing the subselectric field. So we are thinking if we see that distortion and that Harang reversal stays for longer time and is very pronounced for the Steve events, could that be linked to the enhanced electric fields that we see for the SAIDs?
Yeah, that's a great question. Yeah, we do need to know where the Harang is. Well, I guess, the potential pattern that Valerie and Tomoko have shown, that tells us something. The dusk side convection cell will shrink, will get shifted to day side. So the Harang is not at the usual place. You can also tell from our super radars. Normally the Harang is sitting, 22, 23 our local time. But we don't see that kind of thing for the Steve substorms, that loop-like oral structures or the sudden turning on the flow has shifted to the dusk side, and streamers are running straight down from the polar boundary or oval to the equator boundary where the Steve is happening. So, so that indicates, that the separation between the day, dawn side and dusk side convection has shifted. So the Harang is also not at the usual place, and that's probably consistent with a different injection pattern or the ring current distribution compared to regular SAP situations. We still don't know why that is happening, but based on what we see from Aurora and the convection pattern that Tomoko and Valerie are doing, we see the same thing. So I think this is real. I think that's a good result we got. So we can start from here to understand why the convection pattern is special.
Do you think we might be missing global magnetotail model where they could change the location of the injection to a more dusk geometry?
Yeah, so that is really needed. I think I remember Tomoko has shown some strange dusk side geoheating or something for the storm event in 2007, September 2017 storm, I guess. So I know that kind of thing can happen. So we're not talking about some weird uncommon situation. We know it can happen. It has been documented. So I see MHD simulations creating reconnections in somewhere very far away from midnight. So I know MHD can do it, but the question is how to control upstream conditions so that MHD can respond in a way we want. If we just give the regular solar wind conditions, then we are not going to see any significant difference between Steve and non-Steve conditions. So we're still missing something.
I agree. Yeah.
But it's I felt encouraged because I thought this is in a magnetosphere process, and then we are most of the data that we know how to handle. We actually going to include more mid-latitude superdam. I'm working with Mike Uronomi and then Shivaji Chakraborty. Maybe I'm mispronouncing his name, Chakraborty. So we're going to do that, but I feel encouraged by that discussion right now. That might be tail doing something. Yeah. So we're gonna. Yeah, I love to interact with this group more. Thank you.
Yeah, that's great.
Any more questions for Tomoko or Valerie? Excellent. So maybe thank you to all the modelers. I think we're still missing Evgeny Mishin. Probably he's still in his phone call. But I wanted to ask Jun Liang if he wanted to show something. He mentioned something earlier.
Hello, I'm actually having lunch at the moment. So can you give me maybe about 10 minutes?
Sure.
So Bea, maybe we could just spend like a couple of minutes, I think, as you suggested somewhere else, looking over all of these modeling results, and can we pull out some common threads, kind of like we did from yesterday? Somebody want to take a crack at that? Doesn't have to be me or you. Could be anybody else.
It's just slightly different than what you just brought up, Phil. But I'm curious with I've heard a couple times in the last couple days discussing, this interest in Steve and these investigations in Steve as an interesting way of approaching advancing the understanding and the science of subaraural ion drifts. And I just wonder, I think this last study was an excellent example of, would a reasonable next step be, are these properties that we're seeing true of all, is most subaraural ion drifts over a particular threshold? Is this something that can be generalized to said in general, or is this a Steve specific thing?
That's actually an excellent point. You are trying to make a statement about the general case, which is kind of tough. Do we have the observational resources necessary to even attack that? I don't know. Like, then again, we're trying to get citizen scientists involved here, and maybe that is the next step, to get enough additional information, Bill, that we've got enough data to be able to make a statement one way or the other there, because I think that's really important.
Right. Yeah. Because if we can make a statement about, if we make a statement about Steve specifically, and then rather than having a study on 32 or 64, Steve events, is like, okay, do we have timestamps for 1,000 subaraural ion drift events to make and see if these same patterns sort of, remain true.
Right.
There are some statistical studies of SAID, like Hierov, who have used DMSP to make hundreds of SAID event lists. So if Valerie and Tomoko can take that sort of SAID event list, and you can see if that distortion of potential pattern is happening for SAID events in general, or only for intense SAID where Steve is happening. So that is kind of doable research, because the event list does exist.
Right.
Yeah, sorry.
I was going to say,
mention.
sorry, you first. I've just, Liz put in the chat another SAID stats paper that could be looked at, I guess, Liz, right along those same lines.
Just the one Toshi just mentioned.
Oh, that's the same paper. Got it. Okay.
Yep.
Great.
Yeah, I was going to ask Bill if he could. I know you have a list of SAIDs identified from swarm data. Is that a public list of SAIDs that maybe Tomoko could use if she wanted to model those?
Yeah, I mean, it's not all that many events. It's only about I can't remember the exact number, 120 or something.
Identified by swarm, right, Bill?
Yeah, they were all SEDs identified by swarm.
Mm-hmm. And then we hundreds. Okay, I know, right? Much more. Still need to push the button, but I think it's one way to see it. I think it's just really the it helps. I think it just help us to connect the dots. I think because we could say something about global patterns, may not have associate Steve optical observations because we might be missing this, but
Valerie, maybe you could comment. You did 64 cases, 32 Steve and 32 non-Steve. How much of a crushing workload was that? I mean, if someone's going to ask for an order of magnitude more runs, are you going to fall over weeping, or what? You know, I'm just trying to see how heavyweight these are.
I ran all of these events on a version of AMGO that is not the newest version. So it was a lot more time consuming for me than it would be using the newer version of AMGO.
I see.
Yeah, that being said, some of these events, since it's 5-minute resolution for a 3-hour duration, it can take up to like 45 minutes or an hour for one event to kind of finish running. So it can be kind of time consuming just with the run time for each of the events. But yeah, it's better now than the version that I was running. These ones
Sure.
a little bit manual, so that did take quite a long time.
Right.
Yes, one thing that we did for not really available as a open source version, the amateur run, that we actually use DMSP SSJ data to get a better conductance specification. I mean, you know, DMSP comes and go, and yeah, those are done by hand. I mean, well, not really, but it's not
run through one model and then
right.
I see.
That's why Valerie is using older versions, because we originally wanted to include that in a release, but we anyhow conduct. Go ahead.
Well, I was just gonna add that those conduction and dual heating maps for the campaign events are also available in the Google link that Tomoko shared in chat. We have some movies of those events, so you can take a look at what it looks like there.
You know, like talking about this SAID, you know, I think it, you know, definitely maybe like not like hundreds events, but like because we did the 32, maybe I don't know why there was not 30 and 32, but I think that's what Bear's list, I guess. So we're carrying that number, but so you know, then maybe you could look at that, you know, AL, so that make sure that those are equivalent in terms of the currents. But you know, we could do something like that, and then if that's really helpful to address that, I guess that's what we're talking about. And then I maybe could feed that into those global model or regional models to see what happens. Does the emission or precipitation heating happens or not consistently? And then maybe is that something you want to decide to do or can be done, or like once we create those maps, what are you gonna do? I'm just curious. Who's gonna take that? I guess.
Quickly point out that Evgeny is here. Maybe we can finish his talk and come back to this discussion. I'm sorry to interrupt.
No, it's okay. Yeah,
but we could come back to it in the discussion session where we're trying to pull threads together. Please bring that up again. It's an excellent thought.
Can you share your screen, Evgeny?
Yep.
Well, we are switching screens. I just want to say that Valerie has an awesome paper that she's about to submit. It's a very detailed paper, so I know probably some of the reviewers might be here today. So any of you could be a reviewer, that's what I'm saying.
Right. So while Evgeny is hopefully you can hear us.
Yep.
There you go. Okay, Evgeny, we know you had some stuff that you wanted to say, so we thought.
Yeah, I would be glad. Okay, I try to share screen. Okay.
Oh, did it not work?
Share. Let's see.
Oh, it's working. It's coming up. Okay. We can see your desktop.
Uh-huh.
So just
okay. Should I use how it's called, slideshow?
If you can, yeah, some of the details are on my screen are a little bit small. And yeah, it looks like that's a book cover.
Okay, let me start from the beginning. How much time do I have actually? 20 minutes?
The session ends at 5.
Yeah, so when we're at what, 4:35 right now. So yeah, Evgeny, if you could spend 15 minutes or a little bit more, that'll allow a little bit of time for discussion at the end, maybe.
Okay, okay, I'll try. I don't know. I usually short of.
Or we can do the discussion for the second part.
Or we can do that too. Carlos made a good suggestion. If you'd like to just do what you're going to do, and then we can, after the break, we can come back for a discussion if you can make it.
Okay.
Yes, I think so.
I'll try. First, I'd like to show some subauroral forms from above. That's from the Michael Henderson recent paper, you know, and it's very nice images from polar camera in several wavelengths, and it shows nicely development of subauroral form. I just enhanced the images to show you the subauroral forms. Basically, that arrows show, and it's different event, you know, and even he found DMSP observations at the dusk to show the subauroral feature on the dusk. Actually, it's late recovery of strong substorm, and so the very powerful SAPs on the dusk side, and that drives this subauroral feature. And it's a set different colors, just to show you that you know, people observed that, but probably did not emphasize the significance of the subauroral forms. So basically, if you looked at the slide I posted like a couple weeks ago, and I would suggest for Steve, not strong thermal emission velocity enhancement, but suprathermal emission velocity enhancement. And that's because I will show you, I remind you our paper that vibrational barrier inhibits thermal mechanism. And that's why SAR arc and STIF are different in colors. I mean, why red is not so red in STIF. Okay, just to remind you the slide, and I'll go further. Okay, that's STIF versus SAR arcs. You can see that for thermal excitation rate, if you take STIF parameters and SAR arc parameters, you can see that the excitation rate in STIF should be much, much greater than, and it's logarithmic scale, than in SAR arc. So why not? Why doesn't it happen? And it happens because bite out of the tail of the distribution function due to this vibrational barrier, due to basically vibrational excitation of N2. Okay, that's and given that N2 density increases inside the trough, STIF-related trough, so that the critical altitude should be like above 200 kilometers for the red to be suppressed. Okay, now I will tell you a little bit about SAD mechanism and why these suprathermal electrons are intrinsic feature of SAD-related events, not only during substorms expansion, but also in the recovery phase. And that's, we can see the plasma sphere boundary layer created by earthbound hot plasma jets, or BBFs, bursty bar flows, or mesoscale plasma flows ejected from reconnection from the merging point or merging area. So that's nice schematic, I like it. And you see this hot mesoscale plasma flows hit the plasma pores, then there is they are short-circuited by cold plasma, so that electrons, hot electrons, stop here and create very sharp plasma sheet boundary layer, but ions penetrate inside, and this charge separation, so to hot charge separation, so to speak, creates electric field, which is SAD. And the quasi-neutrality here is maintained by the cold plasmaspheric plasma. Why it is called short-circuiting. So the cold plasma short-circuited or shorted out the polarization charge, and that creates all this stuff, this SAD stuff. All right, so that's substorm injection, just to illustrate connection, etc., and the conditions for this process, so that to happen. It's a very benign condition on the density of the ejected hot plasma jet. Sorry. Okay, that's some examples. It's from cluster in this event. Here you see a cluster crossing dipole field line somewhere near L.5. It's inbound and outbound. Almost simultaneously, polar crossed the same flux tube a few minutes later, and DMSP here also a few minutes before, right? So what you see on cluster is this here. Basically, here the channel characteristics here and outbound orbits are basically the same. All 4 cluster satellites crossing, in sequence, basically show the same, very same features. So what is important here is that at the plasma pores, here the plasma, you see the density, the plasma sphere here and the plasma sheet here, very sharp boundary. You see very powerful enhanced plasma waves from proton gyroharmonics, or emic even below, up to and above lower hybrid frequency here. So this is SAD electric field. This is because cluster shuts off the electron detectors. They have only electron counts of 1 kV electron count, so that drop in this kV counts. And this is ion, very typical ion nose penetrating inward into the plasma sphere. Polar is about the same. You can see very nice sharp plasma sheet boundary, this ion nose here, and the same density profile right here at about 1 Earth radius altitude. And DMSP, oh, I didn't show DMSP. Anyway, DMSP shows practically the same as polar, except of course plasma density. And the matching is when you map it from cluster to polar and then to DMSP, you find excellent mapping with accuracy of about better than 10%, I mean, in the electric field. So showing that there is no any potential drop in the flux tube. This is another event. It shows about the same, and it's approximately the same configuration. The only difference that the electric field here is much twice, almost 3 times greater than in this event. And basically the energy of pressure of the ion flux is about this, twice as much as during this event. And this is, you know, recent storm, St. Patrick's Day storm, 2013, I think. I don't see. Yeah, 13. And you can see this characteristic feature, very sharp spike in the electric field, say the electric field. It's about 35 millivolt per meter now. Very sharp electron plasma sheet boundary, the characteristic nose, and a spike in the wave plasma turbulence right here. And this is basically a very robust feature. And at different, you know, this is at L at about 3, this L5 here, and L4.5 here. So during individual substorms and during storm time substorms, which is here from Van Allen probe. So this is very robust feature. What is the cause of turbulence? Funny. I don't want that. Okay. And the cause of turbulence is very sharp pressure gradients in this boundary layer. You can see here fine structure of the plasma sheet boundary. This electron pressure and density near the plasma pores. This is plasma sheet from polar and from Van Allen probe. You can see very sharp spike in the electron pressure. Basically, it's due to piling up of hot electrons that are stopped near the plasma pores, near this separatrix between auroral and subauroral region. And basically, the influx rises the pressure, rises the number of particles, rises the pressure. And so in the steady state, this influx is balanced by azimuthal drift. And this azimuthal azimuthal drift, actually electron current, which is shown here and here and here. So that this current is so intense, it's intense, and in other events it's up to 100, 200 nanoamperes per meter square, which is almost 10 times greater than normal ring current. And this current drives all these plasma waves, which are shown here, different frequencies, emic, or hybrid, fast magnetosonic waves. What is essential that this pressure peak, electron pressure peak, lasts for more than 1 hour, as shown here. The THEMIS satellites across this area, this boundary, in succession. So the last one, I don't remember which one. Okay. A, B, C, D, right? And A crossed in about 2 hours after after the first two, and this one closed in an hour and a half after the first one. So that the peak, which is shown here, I don't know whether you see or not my arrow. Yeah, here existed for at least 1 hour. And so during, and there was a substorm recovery phase. So that's the source of turbulence. In the boundary layer, another source is the pressure gradient of the ions, of the hot ions. it's basically the inner edge of the ion injection into the plasmasphere, or you can tell it ring current injection. So this pressure gradient we discussed 15 years ago, based on the CREST data. Now it's another satellite available, as you can see. And this pressure, the ion diamagnetic current is strong enough to drive turbulence as well. And in between, in this area, the driver of the turbulence is the anisotropic distribution of the hot ions. So that three drivers supply free energy into the turbulence. Oh gosh. Okay, so that this turbulence heats particles, ions, and electrons. Not only their thermal energy increases, but also it accelerates. I mean, the feature of this turbulence, especially the lower hybrid turbulence, is particle acceleration. So suprathermal tails up to a few hundred eV appears here. And you can see it. This is energy from 1 to about 400 eV in cluster, polar, and Van Allen probe. And you can see this hot zone in the ion distribution from both. And you can also see these suprathermal electrons. It's 100 eV here in these two events. And so the same, basically, very same feature it's SID events, but the same feature is true for SAPS events. Heating and acceleration plasma particles in the plasmasphere, very fast heating in less than a few minutes, basically. So no collisional mechanisms can provide such great rate of plasma energization in the plasmasphere. Okay, so now let's go to Stephen Pick and Fence, Toshi Nishimura, and other events. So that's schematic from our paper 2019, and you can see this two SED events, pink and green corresponding to Steve and green fence, or picket fence. All right, so this scenario of double SID, that's basically based on our scenario of how the plasma sheet, how this hot plasma jets or mesoscale flows stopped at the plasma pores due to short circuiting. I told you. So one injection, if you have another injection, then the plasma pores should move inward, and then during recovery, it expands backward, tailward, so that some of the electrons get trapped inside the plasmasphere. And that's it's nothing known here. It was observed by Kress and explained by Bill Burke back 20 years ago. So it's just the same scenario. And it's when you look at the sorry? Okay, I continue. When you look, for example, here, snapshot.
Could people mute if they're not making a comment?
So when you look at the, for example, so-called streamer events after substorm, stop. Who's red? Do you have a question or what? I mean, don't.
Evgeny, right now, the only open microphone is yours.
Oh, really? Because I hear something. And,
yeah, me too.
Okay. So when you look at the events related to auroral streamers, post-onset auroral streamers, which are shown here. Someone.
I think that might be your. You sure that it's not your computer? Literally, you're the only person with a microphone open.
Do you have the YouTube open somewhere?
Oh, yes. Liz might have it because the YouTube stream is delayed.
Okay.
You're feeding back to yourself.
I think you got it, Liz.
All right. So when you look at the auroral streamers, this is onset. This one streamer, then another streamer in one event on March 2008 from Toshi's paper. And when you look at the pertinent DMSP orbits, which fortunately were right at the same magnetic tube in the near time, you can see that this is gosh, I can't. This is SAD, right? This is plasma sheet boundary. And it corresponds to O onset. Then streamer, first streamer. And you see that first SAD moved into, remains in the subaraural area at that time. Second streamer is here, and onset is here in auroral area now, because the plasma pose moved inward. And that's one event. In another event, basically there were onset and four streamers available, but due to the time delay, due to streamers propagation, what the heck? I don't know what happens. Anyway, so that's basically in line with this observations of streamer-related DMSP, fast flow SAD, and precipitation. Okay, so why? Why is the precipitating electron flux so important for the creation of the picket fence? And that's also from our paper. Anyway, so ionization in the E region and related Pedersen and Hall conductance strongly depend on the spectrum of the precipitating electrons. That's well known. It's a Robinson formula, for example, which defines the ratio between Hall and Pedersen conductance on the energy of the average energy of the precipitating electrons. In the green spectrum here, you can see the significant amount of energetic electrons, and this area designates electrons penetrating into the E region. So for the green spectrum, this ratio is about 2.2. For the pink spectrum, it's less than 1. And why is so important? Because when you look at the what happened?
So Eugene, if you can wrap up a couple of more minutes.
Yeah, sure. Okay, I don't understand why some slides.
Yeah, we're right. We're right at the break. So
okay, so basically what I want to say is that energetic electrons absorbed during this green fence event And the absence of such energetic electrons during stiff events is the critical signature, critical difference between the formation mechanism of stiff and picket fence. And I want it illustrated by some formulas, but okay, I'll stop here.
Okay. Thanks, Evgeny. That's a lot of pulling together of things that we already knew in other contexts and applying them here. I think that's really quite valuable.
Yeah.
I'm going to ask one very quick question here, and then I know we have to take a break. When you have both the picket fence and Steve occurring at the same time, right? Are they spatially separated, or are both of these things operating at the same time? In other words, if the mechanism says, okay, Steve are different than picket fence in terms of the energetic electron spectrum, how does that all work?
Well, basically, I think that they are okay. When you have two SAD structures, right? Then one structure with electron precipitation creates creates both structured stiff and picket fence at different altitudes. If there is no precipitation, then of course you have only stiff.
Okay, thanks. That helps. Evgeny, I've had a request because there's a lot to discuss in what you have there. Maybe we could pick up the discussion a little bit after the break. I think that would be very good.
Yeah.
Great. So just to remind everybody, we are at 5 o'clock or a little after it. So we're going to take a break from now until 6 p.m. Local time. Bea, I think I have that right, correct?
Yes.
And come back. We'll have some comments on Evgeny's, and I know Jun Liang has just posted also that he's got a few slides to talk about at that point as well. Are we doing the Gather Town thing again in the break here?
Yeah, if you want to do it, I'll probably be drinking some coffee and eating some dinner.
You may see a few people show up in the latter part of the break, but let's continue the discussion. This has been great. See you in a little bit.
Bye, everyone. Hi everyone, it's after 6 p.m. So I guess we should start the next session. Hi Evgeny, how are you?
Hi Bea, good, good. Listen, I actually want to discuss the colors of Steve, and I'll get a few minutes, would be great.
Sure.
Yeah.
That sounds perfect. Yes. Yeah, we have, I think we discussed having a little bit of discussion related to your talk now, and then we will have June showing us something, and then we'll do the campaign events. So we have time for it.
Okay, so a few minutes about the colors.
Perfect. That sounds perfect.
Okay, share screen. Yeah, sorry. Okay, where is it? Yeah. All right. So in this paper, in 2019 paper, we basically showed that reactions considered by I don't know, it's ad hoc standard reactions for the night chemiluminescent and radiative attachment are fail to explain short wavelengths part of the continuum in Steve. So basically, these reactions are good for explaining like red part of the spectrum, or like above 500 nanometers, 550. But they basically, the rate goes to zero at about 450. So there is no way to explain that. This reaction, endothermic reaction, which was proposed to explain some continuum in artificial aurora back 40 years ago already, also fails because it has a cutoff at about 500 nanometers. So so that the only way to explain this continuum is to include vibrational transitions. So that's basically this kind of reaction and that kind of reaction. So first and second positive bands of vibrationally, electronically excited, vibrationally excited electronic levels of M2. And the laboratory experiments give really very good evidence that this should work. This should work. The reference are given in this paper to laboratory measurements. So we need also a possible reaction of quenching NO2, which gives also a good part of the spectrum. So to explain NO2 production, you need nitric oxide, basically. And the nitric oxide can be created in vibrationally excited plasma by these two reactions. So that simply a high level of the ground state of M2 and electronically excited at 3 signal U. And these are calculations for Aurora, actually, back in 1987, which show that, yes, indeed, you can produce a lot of NO in the heated and vibrationally excited plasma. So that NO amount can be as high as O2 and that gives you enough to explain at least high infrared radiation from aurora. That's one point. Another point is, sorry, to look at the green fence. You remember that I mentioned when you have precipitating particles, precipitating electrons, then the whole conductance can be greater than Peterson is by a factor of 2. And that's the conditions for the Toshi-Nishimura event with the green fence. And that gives possibility to create such columns of rays in the field-aligned current due to so-called positive feedback instability or anospheric feedback instability. So that the difference when you have sigma, when you have Hall conductance 0, so no precipitation, you have nice latitudinal structure driven by this SAD electric field. So that several strips, like Steve-like strips, and when it's sigma, when the ratio is about equal to or more, you have nice columns of, I don't remember which one, up and downward directed small scale current. So the order and the size is a few kilometers. So that's very important. So now I want to promote our book, which will be published soon, hopefully in November or December in Elsevier. So we discussed all this auroral and subauroral stuff here. Anyway, so remaining questions for the picket fence. First of all, I agree with Mende and Turner. Indeed, the ratios of green or blue to red or blue to green ratio in picket fence is different from usual aurora, and that's kind of a question: how to produce this unusual color on the picket fence. But it's not unique, you know. Back in, let's see, 89, I think 86, Tom Hellin and Nielsen, Hans Nielsen, reported on such kind of spectra is a lack of blue in normal aurora. And that is example, one of their examples. It's a thin layer, so-called HEM, which is only 5 kilometers. Here, this is 15 kilometer scale, so it's a few kilometers thickness. And there is normal aurora, and this is HEM. And there's a series of such events called enhanced aurora. But what is important for this kind of spectrum? It's one example, it's another. This is HEM, and this is usual aurora. That you see enhanced red color. And basically, this is second positive and minor bands in this spectrum. And of course, they invoked suprathermal electrons between the threshold for the so like 7 eV and less than ionization, 1875 eV, to explain this spectrum. Basically, in my in the past, the explored collective effects, so turbulence effects in aurora. And basically, you can find the conditions, especially at this altitude of the E region, where turbulence, Langmuir turbulence, created by the precipitating bump and tail distribution of energetic electrons, that you have acceleration, but the maximum energy of accelerated spectrum is below ionization, because ionization is a very serious, very powerful energy loss process, so that the pumping from turbulence is not enough to overcome this inelastic losses, so that accelerated tail just stops here. And so if you remember, if you recall the spectrum of the of energetic electrons in the event, where it is? Here. So this green, you see, there is some indication of the presence of a kind of a bump, like bump and tail for such electrons. So it might create a very weak beam plasma instability, so that Langmuir waves can be generated, but sort of in a weak regime, when you have some acceleration, but not enough to overcome this inelastic losses, ionization losses. And that is exactly what is needed to explain such low green ratio, low blue to red ratio. Another way, which probably is even more plausible in my point, is that there in this current, if you look at the numbers, you see it's more than 1 microamp per meter square, and it's driven only 50 millivolts per meter electric field, while in Steve you have more than 200 millivolts per meter. Okay, so the current should be much greater than 1 microamp, and it is huge current. Basically, if you take it for the Steve typical density, like 10⁴, then the current speed would be huge. It would be 10% of the thermal velocity, electron thermal velocity, which is well enough to create ion sound instability in this strongly non-isothermal plasma, where electron temperature much greater than the ion temperature. So that this creates anomalous resistivity, especially in the downward current region, because in the downward current region you have density hole in the E region, so the density is depleted even more, because its dynamo, its mechanism is well known. So in the E region, you have a hole in each green, in each yellow, say, spot. So you have multiple spots, multiple holes in the E region where the current is closed. I mean, field-aligned current is closed by Peterson and Hall current. So that there is no surprise that, for example, streaks are kind of are not, they are connected to, but not follow the pickets. You see. Another point is, which is probably more important for pickets, is that there is a valley. A quiet time density profile has a density cavity at altitudes between above 120 but below 140 kilometers. And this is well known, it's called valley. A lot of statistical studies on that. So here the density drops to about 10 to 3 particles per cubic centimeter, even smaller than in the F region trough related to Steve. So for these densities, and for such, even for 1-2 microamps per meter squared currents, field-aligned currents, the current velocity exceeds electron thermal velocity in this area. And so this is a well-known condition for the Buneman instability. And the Buneman instability is well-known source of double layers, which create basically accelerated electrons. It's a charge, double layers, you probably know, it's a space charge. So that here, probably the area of the region of generating suprathermal electrons needed to explain green line excitation. Okay, now see various streaks here. So mysterious streaks, and Josh presented very nice review of his paper and future. Just an example we use in this book in the last chapter. So again, I mentioned that about the holes in the dynamo region, in the region of closure, which is about 105, 110 kilometers altitude. So at least tentatively, it helps to understand why the pickets and the streaks do not move in unison in concert. Another, there are few possibilities. I just state them without maybe analyzing. It's not enough time it wasn't enough time to analyze the importance, relative importance of each effect. But remember that these field-aligned currents are actually a signature of small-scale inertial, so-called inertial Alvin waves. And it is known that there is a, for these values, it's already enough to exceed threshold that the uniform wave pattern splits into so-called convective cells. So basically you have local mesoscale vortices in the convection of the and the electric field, radial electric fields basically is created from
if you can wrap up.
Yeah, that's it. So that's another possibility of creation of such small scale structures. That's it. Thank you.
I'm not the moderator for this session, but are there any questions for Evgeny?
Well, lots of questions. This is a lot to think about. I would just want to go back to maybe a lot earlier where we were talking about precipitation driving the IFI. I'm just wondering how much actual flux is needed to make that instability be operative, and why, maybe some overflights didn't measure that, like in Bea's papers.
Basically, this instability is driven by the electric field, by the SID electric field. And it requires also low conductance in the E region, relatively low. say 10 to 4 particles per cubic centimeter. And the threshold for the electric field is very low, actually. It's like 20 milliwatt per meter. So the stiff condition, say electric field in stiff or flow velocity is well above this threshold. So that's no question that it can be driven there, can excite. Now, why conductance is important? The precipitation energy, if electrons can penetrate into the E region, so the average energy is greater than approximately 4 keV, then the whole conductance will be greater than Peterson conductance. And so the two-dimensional problem becomes three-dimensional, because the current can be closed also by the whole current. Okay, so the nice meridional electric field will be split into meridional and azimuthal field, and that creates basically the reason for creating such longitudinal structure.
Just follow up, but it's true that this requires precipitation, and I'm just wondering if the flux would be measurable, and why no overflights have actually measured it.
What? Well, electric field is measured, right?
But the precipitating flux, I think.
Precipitated flux.
Yeah.
But okay, I showed it a couple of times, showed another time. This is electron fluxes from Themis.
Mm-hmm.
In the event at green is the event where green fence.
But that's not entering the atmosphere, right? This is at the plasma pause.
Yeah, but well, it's, as I said, okay, let me show you this. No. That, okay. That's this two SID events measured by Themis and measured by the MSP, which are conjugate, okay? In this green SID, a green color SID, energetic electrons are measured by Themis. Here, in this case, there was no energetic electrons. And this structure is conjugate to the green fence. And that structure is conjugate to the stiff structure, to the stiff arc. So back to spectra, you see the difference. The flux, the measured flux is greater than, several times at least, greater than in stiff relay. And black, this is a typical spectrum for just normal SID from one SID event. So that I just showed it to emphasize that the slope of suprathermal particles in all events is about the same, and this is due to acceleration. But energetic particles that can penetrate into the E region is quite different. And when you calculate, for example, conductivity ratio using well-known Robinson formula, and this is here, then you find that for the green spectrum, you have this ratio. But for that, you have less than 1. Is it clear now?
Well, not entirely, but I don't want to hold up.
Yeah, let's go. Yes, sorry. Liz, you have your hands.
Yeah, I had a question, and I want to thank you for sharing all of this insight with us. And I'm sure that I don't understand all of it, but I wanted to ask, in terms of your predictions here and the connection to Steve and the plasma pause, do you think that your explanation applies kind of only in the subaurora region, or do you think that some aspects of describing Steve or the picket fence also apply more so in the higher latitudes?
No, basically, you know, all this subaraural stuff is based on our work in Aurora. And it has a long history, starting from active experiments with electron beam injection back in the 80s. And so with regards to, you know, collective mechanisms, or collective means, say, unstable processes and their effect. And unstable is, first of all, beam related, energetic electron related, excitation of ring mirror and upper habit wave, harmonics, and field aligned and transverse currents related turbulence. Basically, that's kind of, there is no difference with subaraural, with approach to subaraural events. The only difference, of course, is the, first of all, is there enough flux? Is there other distribution functions similar or not, etc., etc. But for field-aligned currents in, for example, subaraural area, in Steve, for example, it's the conditions for instabilities are even easier than in Aurora. That's why in Aurora, for example, it requires very big currents, like more than 10 microamps per meter squared, sometimes in smaller scale, 100 microamps per meter squared. Here, just a few microamps per meter squared, which is reasonable, and they are observed. I didn't show them, but they are observed really in SID and SAPS events. Because density is very low.
Mm-hmm.
Plasma
Mm-hmm. Thank you for those comments. Thanks.
Mm-hmm.
Evgeny, I guess on slide 19 or so, you mentioned about the double layer formation by Fare-Bunemann. Do you have any thoughts about how big, the potential drop can be due to the double layer?
Here, yeah, I mean that it should not be very large.
Yeah, I'm wondering if that, that small potential drop can be, consistent with what, Stephen Mende is talking about as a cause of small excitation.
Okay, just expectation, because it should be analyzed. We did it, there are different kinds of double layers. Strong double layer and weak double layer. When you have just slightly, when the electron, when the current speed velocity just slightly exceeds the electron thermal velocity, then there should be so-called weak double layers. It means that you have multiple humps of the potential so that the total voltage over the one hump or one double layer should be like of the order of a few electron temperatures. And there are several of such humps in the whole area, in the whole region. So basically, you should expect like 10 of the gain in energy of electrons, coming through this region should be of the order of 10s of electron temperatures, not more.
Okay, I'm going to step in and just ask us to perhaps take those into GatherTown or discussions afterwards. We still need to get to June, who wants to show a few slides, and then on to the case studies or the campaign events. So again, this is just a lot of discussion going on. Jun, are you ready to go?
Yeah. How can I share it? First, I want to share my screen here.
Okay. Looking good.
So yeah, can you see my screen?
Yes.
Hello?
Go ahead.
Yeah. Okay.
Yes.
Yeah. First, I have to say I didn't prepare to talk in this meeting. Well, nothing against the Steve workshop. It's a great workshop, but just for myself, I'm done. I'm so done with the online meeting. I just hate that. Yeah. Okay. So yeah, but it's actually the Canada Thanksgiving storm and the great discussions in the Albert Aurora Chaser group drive me to make some sort of presentation here because, well, okay, this is the Canada Thanksgiving storm, and the Alberta Aurora Chasers have contributed a lot to this. So I think it's our responsibility, well, I mean the University of Calgary, to give the first scientific talk about that. So yeah, so a number of people have talked about one of the major unresolved mystery of Steve, that is the continuum spectrum. So this is from Gillis' paper. Yeah, the major source of the Steve's luminosity comes from the overall enhancement of a continuous spectrum spanning between, well, roughly between 400 to 730 nanometer, which I term it as a air glow continuum in my paper in 2019. So yeah, this is from my paper. So I just briefly mentioned the OXO multispectral imager at Athabasca, which will also be used in this talk. So it contains the typical aurora emission lines, such as the green line, the red line, and the H beta, and two background channels, the 620 and the 480 nanometer. So yeah, for that event, we also have Rigo and the tracks, but yeah, and the FISL. The FISL also contains the H beta and background channel. So I'm not going to enter the details of that study. You can just check my paper. So yeah, I just mentioned two things here. First, both the Rigo and OXO red lines see the Steve and the SAR arc. So this is the kind of the red line features here. And for the background channels, the 620 and the 480 nanometers, they are used as the proxy of the air glow continuum here because they are the background channel of the aurora lines, but they can measure the continuous spectrum, the continuous spectrum. So they actually showed us the Steve. If you look into details, they actually exist as a double layer structure, but I'm not going to enter the details of that today. But just a quick mention that the Steve does appear on the background channel. So yeah, this is a photo from this event. This is contributed by Neil Taylor, my friend in the Alberta, the Aurora Chaser. So in short, the Steve show up on both the signal and the background channels. I didn't plot the signal channels here. I just plotted the background channels here. So, but this is not proton aurora. If we subtract the background channel from the signal channel, yeah, the pure proton aurora intensity is practically zero. So, but the Steve does show on the background channel. So in contrast, we notice that the SLR arc does show nothing on the background, the basal background channel, but the Steve does show. That means Steve contains a kind of the continuous spectrum. That's because. So it does show up on the background channel. So as Liz mentioned yesterday, so this Canada Thanksgiving storm contained many kind of the interesting, and the mysterious the aurora and the irregular features, such as dunes and SAR and Steve, and of course the rings. So unfortunately, at that night, I was busy with my presentation. The SMILE meeting was starting from that midnight. So when I saw this picture sent by my friend, I realized that what I have missed. So yeah, I'm not talking about Steve today. Yeah, but trust me, there's something very similar to Steve. That I'm talking about these ring structures. So there are many kind of the very fancy, very amazing photos and videos available made by the citizen scientists. So I'm just wondering, what does it look like on the scientific imager? So for example, Oxford. So yeah, first of all, quite unfortunately, the Oxford green line imager, which is the most, of course, the strongest aurora emission lines, that saturates for the structure of interest. We can see some sort of undulation here, which may correspond to the ring structures, but we can't see any details of that. But on the other hand, was the red line 630 and 620 and H beta the 486 and the 480 the imagers are useful and provide very interesting data. So okay, so I want to emphasize again, the 620 nanometers is designed as a background channel for the 630 red line emission. So I give a comparison between the 630 and the 620. So on the left side, we give the typical red line auroras, and also includes this is the SLR arc we are talking about. Many people are talking about. So this is so-called a stable aurora red, but as pointed out by the Carlos yesterday, it's not a structure, any kind of the structureless the arc at all. Yeah, there are some interesting discussions in the arbitrary aurora chaser group on whether it's a SLR or Steve. So yeah, my verdict is clearly, so since this arc is not shown on the 620 nanometer channels, this is not Steve. So yeah, we'll just recall that again, the Steve has imprints on the background channel. So, okay. So I'm just going to show the 630 and the 620 nanometer data side by side of the facilitated comparison. And I believe you will be amazed by that comparison. So before 413, there are some kind of the strong red line. For example, this arc, you can see this is a strong red line auroras here, but the background channel remains very weak, basically nothing. And something interesting happens after 413. Yeah, I hope you can see the rays in the background channel here, the appearance of something here. So it becomes more visible in the background channel, and the ring structures, yeah, began to emerge here. As you can see that here. Yeah, that's the ring structures there, and so it appears that the red line auroras is composed of a bright arc, and together with some sort of the ring structures. And it's also interesting to note that the bright arc itself doesn't show up in the background channel, but the ring structures does show up. So here we go. So that's if you haven't seen the event, you immediately realize how beautiful they are. So yeah, this I personally have never seen such a strong features in the 620 nanometers because it's designed as a background or a background channel. So but as you can see, so this is the kind of the red line or the bright arc itself doesn't appear, but the ring structures beautifully appear in the background channels. So yeah, here we go. This is just coming. The times goes on, and the ring structures. We can see I can even see the evolution of them. So yeah, okay. So yeah, I think after 420, those sort of the the ring structure that evolves into a kind of the meandering arc, which is so yeah, this is arc forward the red line arc. So this the arc it doesn't show here, but this the forward arc does show on the background channels, as you can see here, the comparison here. And yeah, so yeah, this goes on. So I'm not going to details that, but just remember, this is very strong. This is very strong in the arc in the background channel. Here. Okay, so well, admittedly, so there was some kind of leakage. We're talking about our background, but well, due to the spectral design, they always have some sort of leakage in the 620 nanometers. And we also realized that the 620 may also contain a little bit the N21PG, the emissions. So probably, so yeah, people may argue with me. So yeah, this is not actually a background channel. So we look into the 480 nanometer channel. This is more carefully designed for the background channel for the H-beta emission, because H-beta emission itself is a very faint emission. It's very weak emission. So if it's not carefully designed as a kind of a non-aurora channel, it easily override the proton aurora signals. So I give a comparison between the 486.1 nanometer H-beta and the background channel. So basically, we can see the main proton. That's the main proton aurora band. And we also see a kind of a detached, the detached proton arc, which many people realized the existence many years ago. And this actually detached proton arc corresponds to the subaurora green line arc and the blobs. There's a kind of one-to-one corresponding terms there, but I'm not. That's another. That's the topic of another study. But my point is they are not shown on the background channel. So let's see what happens for the ring structure here. So again, before the 413, and there's nothing special happens. We see the main proton aurora band, but very little thing on the background channel. And something special occurs after 413, and we can see this ring structure begin to emerge on the background channel. And so as time goes on, yeah, that's the ring structure on the background channel, and they are actually very strong. Again, I've never seen that strong signal on the background channel, on the 480 background channel, and it's even stronger than the Steve show up, but it's pretty much weaker. And so yeah, the main proton aurora band doesn't show up here. So yeah, okay, let's go. So yeah, again, after the 420, so the ring structure evolves into a kind of the arc there and goes forward. And again, so this is very strong and very thin. There was one thing I want to emphasize that just the infer from this sort of the narrow structure, it can be proton aurora. The proton aurora usually is much thicker than thicker than that. I will not mention the reason of that. So this is typical of the proton aurora. But this kind of
June,
thing,
if you could wrap up, please.
Okay, yeah, just quickly wrap up. So yeah, okay, so just quickly wrap up. So yeah, this is the basal data. So if we show this kind of structure in both the background channel and the signal channel, but we subtract the background channel from the signal channel. So this ring structure and the arc, the meandering arcs, the forward of the proton aurora band just totally disappear. They disappear. So yeah, so what we have inferred from this sort of the preliminary study here and compared to Steve. So the rings is a forward of the main proton aurora band. So yeah, that's auroras. So it mainly contains dominated by the aurora green line for sure. There's no doubt about that. But it also contains very strong continuum spectrum because we're seeing it clearly in the background channel. The Steve the Steve should be equatorial. There's a kind of typo there. It should be equatorial of the main proton aurora band, and it contains the red line thermal emissions plus a strong continuum spectrum, as we have already indicated. So I'm still waiting for the spectral graph data to confirm these findings. So my question is here. So are the continuous spectrum from the Steve and the rings the same mechanism? So this echoes well with at least the question. Is the kind of the same mechanism works well in both the plasma pulse region and also at higher latitude in the aurora region? So on the other hand, I just want to quickly mention that SAR and the detached proton arc don't have the continuous spectrum counterpart. Okay, so thanks.
Okay, thank you, June. I want to actually forego comments and hopefully everybody can remember this and save them for tomorrow's session, afternoon or evening session, which is colloquially referred to as the "What the heck was that" session, because what June is showing here is I think a perfect fit. June, are you going to be available to perhaps field some discussion tomorrow evening for this?
Yeah, sure, no problem.
Perfect. So I think you gave an excellent preview of what's to come tomorrow, starting at 6 p.m. So I think now we're going to proceed on to the let's see, it's day 2, the campaign events. So Bea, I believe, is going to lead that discussion.
I'll be showing some plots, but I can share my screen. Can I ask a question to June?
Mm-hmm.
I wanted to ask this to Megan yesterday. So you were saying that what I'm confused about is you were seeing Steve in the H beta emission line. But when we did the work for the science paper, one of the points that we used was that we couldn't see Steve in the H beta. And is that because we were over filtering the background?
No. Steve appears in both the background channel and the SIGT channel, but you will subtract the background channel from the SIGT channel. The pure proton aurora intensity is 0. There's no proton aurora. There's just ergo continuous spectrum that appears on both the background and the signal channel of our instruments.
I see. Thanks, June.
So that's consistent that there are no energetic electrons.
Yeah, for the rings, I believe there are. It is in aurora, but for the Steve, that's an open question. Yeah, but for the ring, I believe there will be.
I have a short question. Why is called ring? It looks to me like an omega.
Yeah, this is because okay. Why it's called a ring? So that's why it's called a ring structure.
It looks like an omega, you know. Or
but there are better pictures. There are better pictures from this community. For example, I didn't pick up the best pictures. Yeah, the people tend to call it a ring structure. I don't know what's that. I have no idea how do we call that. Maybe it's just another Steve.
No, to me, just example of Kelvin-Helmholtz.
Yeah, probably. Very likely. Yeah, I agree with that.
Basically typical for when you have electric field.
Were you thinking that this could be an omega band type of thing?
Yeah.
Well, I thought these are kind of, curls or falls that Harinan talked about. To me, these are often happening as an extension of substorm onset Bs.
Okay, we can move on.
Right. Thank you,
I'm
June.
sharing
Thanks,
my
everybody.
screen now.
Yep, go ahead, Bea. Thank you.
I think you can see the PowerPoint. Yes. Right, perfect. So one of the things that we wanted to do is look at events that we have all analyzed, and that's the March 26 to 28, 2008. And the other one is the event that is driven by citizen scientist data. The second event actually is really interesting. And both of them might be related to a small storm happening. For the first one, after the first Steve event, and for the second one, the storm happens. Hard to tell, but or the day before, or the day, or September 1st. So we will look at that. As I told you before, yesterday, for the first event, we have a very intermittent Steve happening on 2008, March 26, between 7 to 9 UT in the Alaska sector. So that's the first interval. All the 3 intervals were observed in Themis ASI. At this time, we don't have REGO. For the second one, this is March 27, 2008, and we see it at this location. And the third one is observed in 2008, March 28 in this location. So one of the things that I asked Toshi mainly was, what are the conditions for us to have intermittent Steves turning on and off during several days? And I would like to ask Mike Hanukal if he's connected, because I know he made a comment yesterday to one of Lindsay's question. Lindsay asked, how often do we observe these several day emissions in the data set? I can answer that from the limited scientific observations, but I would also like to know from the citizen scientist perspective.
Yeah, as far as I remember, there are a few cases with 4 or 5 consecutive days with reported Steve. I have a list prepared where you can have a look at them. I can share a link to that list so that everyone can look for days with consecutive reported to Steve in several days.
That'd be great, also because initially we started analyzing this, the second event, the 2016 September 3rd, and you texted me that there are actually observations on the 2nd and the 3rd, and that is consistent with when we compare the indices for this first event and the second event. It kind of painted a picture that is consistent in my head, and hopefully you guys will see something like that. But I'm not going to tell you because I don't want to taint what you should be seeing. So my opinion here is irrelevant. So some of the questions that we had is, what makes Steve turn on and off in time? And is there a time relationship for the turning on as the storm progresses, or is this only related to the substorm occurrence? Things that we're going to see are the indices. So I'm going to jump to this slide that you have already seen. And I apologize because I realize that these colors are absolutely not colorblind friendly. So I know in the audience, we at least have one person that is colorblind. So I apologize. But for the first interval, we know that we had Themis data, we have GHOST data, we have DMSP data, and NOAA 18 crossing eastward of the Alaska sector. That's where this event is observed. Toshi looked at Themis data for this event and DMSP data for this event. So when we look at the DST index, and I feel like this is important because although we have been saying there is no relationship with the geomagnetic indices, when we start looking at them by event in a separate way, I think there is something that we might be missing. It gets kind of blend in when we do the whole statistics. So that's why my feeling of doing this is we need to look a little bit more carefully to the details. So if I zoom into the DST index for this March 2008 interval, we have Steve observed in number 1. This is the March 26 that occurs between 7:20 to 9 UT. Then the second time that is observed in Pinawa and the central Canada area between 3 and 4 UT. And then we observe it at Kapuskasing on the 28 between 3 and 4 UT. No, 2 and 3 UT, sorry. Oh, I have it there. When we look at the images, and this is for the first interval. So this is the 2D evolution of Steve. This is around the time where you start seeing Steve, so time progresses in this direction. And you see it persistent for like about an hour and 40 minutes, and then it fades away. These are 2 of the cameras that also Toshi published for this event. This is Kakona, and this is McGrath. This is eastward, and this is the westwardmost Themis ASI camera. When we look at the AL index, this is consistent with what we have been seeing. And I think in terms of the substorm evolution, the conclusion that we have all kind of come across is relatively consistent of Steve being in the recovery phase after the substorm. Feel free to interrupt me or stop me, or if I'm saying something that is not consistent with what you think, please interrupt me. In terms of data that we have, so these are the ones that I have just shown you, just a different color scale. This is Kakona and McGrath from Themis ASI, and we also had the meridian scanning photometers at Gillam. So this is slightly eastward from the Gacona. And the reason we were using this, or I was using this, is because we were looking at the proton boundary from the H beta emission. And this is the Bi2 boundary defined by Eric Donovan in his 2003 paper. So when we keep looking at indices for this event, and this is, again, for the very first interval, the one from 720 to 9 UT, we have the AL index in the first panel. We have Bx, By, Bc, solar wind speed, solar wind pressure, and CMH. Just as a reminder, we have Steve occurring in the recovery phase of this substorm. In terms of magnetic field perturbation, and I think this is consistent with what Toshi has seen and what Valerie has seen also in her larger statistics, is that the BYBZ, BX, there is no relationship between that and the formation of Steve. And that is interesting because previous studies suggest that an asymmetric two-cell convection pattern should be associated with a BY component. And we do see that asymmetry in the convection pattern, but we don't see that association with the BY. So a question for everyone that is in this meeting today is, why are we not seeing that relationship between BY and the asymmetry in the two-cell convection pattern? Any comment? No?
Yes, actually, Bay, I have one on that very last point you brought up. Was there a study done on that? Like, was there a superposed perhaps epoch study to show that it wasn't there wasn't a BY relationship?
Yes, so the study was done by Grocott et al. 2012. Valerie might remember the event better than me. Yeah.
Just to clarify, sorry, again, this no BY dependence or influence on the Steve occurrence or a particular pattern?
So the point I'm making here is when we look at the AMGEO results by Valerie and Tomoko, we do see that the two-cell convection pattern is really asymmetric, and that is also part of the result that we see from Toshi's substorm surge moving very far from midnight.
Okay.
But why we don't see a relationship with BY? Like usually you see a BY negative, I think. Valerie, do you remember the details? I think I'm a bit tired.
We do see it negative for Steve events and neutral or very, very close to zero for substorm events. That's the one difference that we found between, and we did a superposed epoch analysis of all 32 events centered around substorm start time. But even though it was negative BY, it was like 4 nanotesla or something very small. It wasn't a significant and pretty flat too for the duration of Steve.
Okay. Sorry, just this I'm not an expert on this, but the idea is that in general, when you see these offsets or this change in location from midnight, you attribute to the influence of some kind of BY component, right? In other processes. And this is not something that we are seeing here for this event.
Yes.
Okay, thank you.
Any more questions? Any more comments? Okay. So apart from the Alaska sector data, and Toshi also showed this in his study, and I think I have these slides from when I was at UCLA, so these are pretty old. These are super down radar. This is the King Salmon radar. And we plotted several beams, and we saw that narrow flow observed for the SAID that is associated with Steve that Toshi also showed. Toshi also showed, and this is something that we talked about at that time too, that the electron he showed the MSP13 that was in the southern hemisphere, and he observed the evolution of the SAID from before the what we call the narrow arc at that time, Steve, during and after Steve. And we observed that fast and narrow, especially narrow SAID type of flows. And that what we call at that time the power retrieve of the proton precipitation observed by the MSP that is not observed at earlier time before Steve is observed. And that was very nicely summarized, I feel, in his 2020 paper. This is something that I am personally curious about, something that I feel like not many people have talked about, and I'm not sure if people in this session will have some comments, but have anyone looked at the total electron content at the TEC data for these events? This is too fast. No.
Bea, this is Phil. I'll just, of course, we have so much TEC data, Haystack. I don't remember this one in particular. When I first saw this, for those of you on the line, I had asked Bea, I said, you got to watch out because sometimes you can have one receiver, a couple of bad receivers that could kind of provide some points that look like blobs, but in fact are not. That is not what we're seeing here. There are so many receivers that are contributing to that unless something is really wrong and it's hanging in there over so many frames, I think that's probably real. So it's just a note based on seeing some other TEC plots.
You're talking about this center part, right?
Yeah, yep, that's right.
I am really curious about that because I don't see the evolution of it, and I see it staying relatively constant in the 3-day interval. Well,
yeah. So Anthea at Koster, who knows much more about TEC than I do, has discovered certain TEC perturbations that actually hang out over orographic features like mountains. And I wonder if that is a line. So what I would recommend is that we get her this data and check it out. Remember also, this is 2008 when there were nearly not as many receivers as there are today. So you are sort of working against that. But things that appear to be fixed like that, sometimes that's what's happening.
One thing to check is go a few days before and after.
Yep, that's right.
See if that structure stays there, because it could be like a bias that has not been properly subtracted compared to others or something. I don't know.
Yeah, that's what I was trying to refer to, Carlos, is that's the first thing you suspect. And, you can check with Anthea, but sometimes these things don't go away just with that. And sometimes there really are structures that appear to be, geographic feature oriented. But anyways, check.
Okay. Yeah, I definitely need to talk to someone that understands TEC better than me. I have very little experience with TEC.
Send us an email. We'll do it.
Perfect. Yeah, but this is something that I don't think that many people have looked at for these events. And I think since we have so much TEC data, this is something that we need to take advantage of.
Okay.
For the second interval, for this interval, I told you that we had several satellites in the western portion of the US. This happened in Pinawa. Unfortunately, FAST satellite was not working at that time, so we don't have that data. And I also told you that the Pinawa data station in Themis, since this is the early Themis time, was lost. But nevertheless, we could see the time evolution in the 2D. So you see Steve appearing around this time, and then it propagates across the field of view of the camera. It gets fainter around this time, and then it fades away. The total duration is about an hour. And you can see it clearly in the kilogram. This is an hour kilogram from 3 to 4 UT from the summary data of the University of Calgary. And when we look at the AL index, again, this is occurring during the recovery phase of a substorm. When we look at the rest of the indices, again, recovery phase of the substorm in AL, and then very small BX, BY, and BZ perturbation. Solar wind speed slightly higher than the previous time, and this is probably related to, remember that in the previous time we were right before the storm happened, and this is after the storm, this is the day after. And I think this is TC for that one. See, I still have those receivers showing that high total electron content.
Remember also, this is a linear scale too, which is going to enhance those. I'm trying, the maps I'm looking at here is another summary plotter in log scale, and it's really, really tough to see it in a log scale.
Oh, that's good to know.
Yeah. There is a bound, this is what time again? This is like,
this is 3 to 4 UT.
Yeah, so I can tell you there's definitely a plasmaspheric boundary going through, you know, the top of the US at that point. Actually, I could show you something for a moment. This is, you're already on the 27th, right? Yeah.
Do you want to show it for the 26th?
Yeah, I have it for the 26th. So if you'd like me to just, I can just push the right button here. Where is it? Oh, I've lost my cursor. Darn. Okay, so this is our standard kind of summary plot, and you'll notice that this is a log scale, okay, not a linear scale, and it's in the wrong projection, which is a pain in the neck. But if I scrub this backwards here to like here, like, oh, you know, about right there. See that boundary between blue? That's the plasmasphere boundary layer for sure. Right through there. And so, you know, there's the Great Lakes. Here's, you know, it's kind of extending up. And so whatever the plasmasphere was doing on that day, it was, you can see the drop off right here. It's easier to see in a log scale. So the stuff you were seeing in the middle of the country is hidden down here in the log scale, okay? But it's useful to just check these against, and we may have reprocessed this data as well. Sometimes that happens. We also have, I don't know how much line of sight data we have there, but if we don't, we could generate it. So we can follow up on that. But my point is that there's a very clear boundary right here, which is probably the projection of whatever you call the plasma pause at the PBL going right through there. And on this map, Steve appeared where?
This is the first one, Alaska. So it's the lower part.
Okay, so it's up here, but you can see the boundary extending this way. Okay, kind of. So you're probably a little south of the boundary, which is, well, heck, that's kind of where you would expect it to be. So that's very consistent.
Yeah, so the blob that you're seeing is basically unrelated to the observation.
Well, I
mean,
yeah, right. I mean, what you're seeing is the blob is down here somewhere, right, Carlos? And it's right. Kind of what I was focusing on was this, which this is a different binning than the data that Bea was showing, right? It's a different, and this is vertically binned. It may be slightly different, and so it may be helping to emphasize a little bit larger features here. So it's just worth examining, but this data looks pretty good. So I think that we could help there.
Yeah.
But just in the terms of where the plasmasphere boundary layer is, that was my whole point, was that it's quite consistent. So that's actually very encouraging. Back to you.
Perfect. So let me see what all the data I collected, and I'm hoping that people can also show whatever data I know people have more data for these events. So yeah, we check these ones. I'm sorry, I got lost in my own. Oh, okay. So then I have the plots for the third interval, and the third interval is in 2008, March 28. And we had several satellites crossing by. The one I used for my 2018 paper was the NOAA 17 that crossed really close to Capus casing. And we can revisit the results if you want, but if you remember, this is the event in which we do not see particle precipitation in any of the post-17 energy channels. We also have the MSP 15 westward of it, DMSP 17 and 14, and FAST, but FAST was also available but not available. And we had DMSP 13 in the Southern Hemisphere for this event. Very similar to what we observed earlier, this is the Capus casing station. So this is the ISWAR most observation of this 3 period of time. Steve is start observed here, and it progresses for, it crosses the field of view of the camera and it starts progressing, and then it gets fainter and it disappears. And this is the summary plot from the University of Calgary from that station. This is an hour kilogram again. And very consistent, although this is a more complicated, probably substorm. If the onset is around here, and I think that's more or less what we obtained from the SuperMag database, then this Steve event happened during the expansion phase of this substorm. When we look at all the indices, again, we are in the expansion, in the recovery phase of the substorm, recovery phase of the substorm. BX is slightly larger than what we observed for the other events, but BY and BC are fairly small compared to what we will expect, especially for such a strong event. In terms of solar wind speed, that's still elevated compared from the previous first day. And I think that's, again, has to do more with the storm than with anything else. And yeah. For this event, I know, I think it was Toshi who also looked at the DMSP data, but we also look at the DMSP data for this event. This is in the Southern Hemisphere, this is in the Northern Hemisphere. In this one, we could see those fast flows associated with the subarauroral ion drifts that we all know are observed during Steve events. I'm going to skip this one because I do want to get to the last one. We can come back to this if you want to talk about this. So this event, I have it slightly mislabeled because I have put 2016 September 3rd from 4 to 5 UT. And Michael was telling me that this is actually happening in September 2nd. So we do see this happening. It's a 2 interval Steve event and 2 different days. In terms of instruments, we had Firebird that yesterday I couldn't answer the questions very well, so I prepared a slide to orient yourselves. Maybe Gareth can tell us a little bit more about EPOC data if we had it available at that time. And then we also had DMSP 19, DMSP 18 in the Southern Hemisphere, and THEMIS and MMS for this event too. These, since the Alberta Aurora Chasers are amazing, let's see if I can play this. This is by Chris Ratzlaff, and he did a time sequence of this event, the 2016 March 03, and this is a Steve event that he observed in Alberta. This is wonderful.
Wow.
Is Matt Zedergan watching this?
I hope so.
You see, you look at all those.
Yeah,
Matt,
I see that.
Matt, you got your work cut out for you here.
Yeah, definitely.
Yeah,
a lot of structures. It'd be nice to be able to plot like phase speeds and stuff.
I think that's what Michael Honeycomb's been. Yeah, Michael Honeycomb's been doing that sort of thing, and you could certainly do it here. You got the star field, which is what I know what he's been doing. So I think you can set that up.
Excellent. Yeah, that would help, because otherwise I feel like we're sort of playing with models and then making things up.
No, but I remember you showed one of those channels that was very wavy, and you mentioned that there were parameters that you could fix that to make more constrained, and that basically would be very similar to these observations.
And Matt, we can provide you with a lot of these kind of views.
Yeah, that's great. Carlos, you're right. I need to think about this a little bit. So phase in group velocities, I think, would be helpful. Like how fast are the bright structures moving? But I have to think about what exactly that constrains about inputs of the models. It's not completely straightforward, but I know it would definitely help.
This is a beautiful example of the power that you have to decide what to do. So don't be shy and keep working on this. This is great.
Yeah, I won't. This fantastic group. I really appreciated the format of this workshop. You know how much discussion we've had, as opposed to just listening.
I hate to say it, Matt. Your audio repeating is happening again. I don't know why, but we get to hear your words twice.
So Bea, this is a movie of the second event on the 3rd.
Yeah, this is the this is the 3rd or the 2nd? This is the 3rd, I think. Yes.
So to confirm, on the 3rd, the 16th, you had an event at 4 to 5 UT, and then this event from 7:12 to 7:22 UT or something.
No,
like
this observation. This one is observed on the 2nd.
Oh, okay.
And these two are from the 3rd.
And at different times. One is 4:05 and the other one is 7:30 UT.
Okay, so right? There's two. Sorry. So I'm confused. There's two events on the September the 3rd, one between 4 and 5 UT, one at 7 UT time frame.
Right.
Yeah. Okay.
That movie is at 7-ish, right? On September 3rd. Yes.
Yeah. Okay. Yeah. Yeah.
It is interesting that it has, like, we always talk about the structure on the picket fence, but Steve is very structured too.
Yeah.
If you select one point to look at, you can see the luminosity changing inside of it.
So once again, you're talking about 7 UT. Is that about right?
Yeah, I think so. That's the time.
All right, I'm going to see if I can figure out where the boundary is standby, and just before I have to run.
You know about exposure times, and
I think Chris is connected. So
yeah, these were pretty long exposures. I didn't have a great camera with me for that, so those were 15-second exposures. So there's a lot of blurring going on.
I like the very long exposure time, 15 seconds. So if you talk about me or my cameras, that's like, wow, so fast.
These days, I'm exposing at about 2 to 4 seconds.
Yeah, if you could put, you know, in parallel this
yeah, I can do that.
The index, geomagnetic index, it would be interesting to see whether this variation in brightness and form follow these spikes.
The structuring inside of Steve, you mean?
Yeah.
One thing that we were
the index, AL index.
One thing that we were trying to do earlier was to correlate the difference in luminosity, because sometimes you can see it in the Themis ISI and the injections are higher latitudes. It's still very, very challenging.
Now, Bea, maybe you guys thought about it. I'm pretty sure that. So we keep talking about comparing with indices or with BZ, BY, but with the beautiful chain of magnetometers that are all over the Canadian territory, has there been an attempt to look at variations from different magnetometers when you are seeing Steve, and just to see if those, for example, these kind of variations happening can be captured by magnetometers?
Might be, but it's usually no. I mean, all these indexes are built, are obtained from the magnetic data.
Oh no, I know, but those are average. I'm thinking specifically, as Bea is pointing, this event is happening in the eastern part, right? So instead of looking at the index, just look at 3, 4, 5, I don't know, whatever number of micrometers that are right overhead the location of Steve or nearby.
Yeah, basically, if you look at the Z component, for example, it clearly shows the shift or motion of the equivalent current in the ionosphere, which is which closes the field aligned current. So that
there you are. Yes, something like that. Yeah.
I have a question about the timing. So I was wondering if these are two separate events for the September 3rd one, or is it just there's a continuous observation of Steve from 5 UT to 7 something, and we just didn't have observations between 6 and 7 UT? So I see one from 4 to 5, and
this one is saying 7. That's a good question. So this time I got from Neil or Chris.
Maybe that is from 4 to 7:30, right?
That's what Bharat is asking, and I would like to know if that's the case.
Yeah.
So my observations were at 7 UT.
7 UT.
Okay.
Yeah.
Hey, Bea, can I just pop one thing on the screen very quickly before? All right, so you're talking about 7 UT, right?
Yes.
I don't think there's any question where the plasma pause is, folks.
No.
That hits you right in the eye. And so if you go right over here up to Washington State, I mean, you'd have to look at the details. But, and by the way, we have line of sight TEC here as well as the vertical. So we have much more detailed structure in here. So those, by the way, notice the difference between 2008 and 2016. Look at the coverage over the US. You have plenty of TEC coverage here. So that one's pretty clear. And I will drop this in the chat so that you have it. All right, let me do that. Let me stop sharing, or somebody can take it away from me. There we go.
Yeah, so Bea, I wanted to comment on EPOP. So you threw that second event in there from September 3rd, which made me scramble a bit. Let's see if I can do this correctly. Okay, what's multiple desktops here? So yeah, let's just go with this. It may or may not work. What do you see right now? Do you see EPOP?
Yes.
Okay, so this is, for anybody who doesn't know, this is EPOP. It's been up since 2013. Got some instruments that are useful for this type of study. Has a low Earth orbit, 330 to 1500 to start. And now it's kind of degraded. But anyways, things that would be of interest to this type of study is it has a FAI, an imager on board. It has a MAG, the MGF, has a mass spectrometer. IRM has a GPS occultation, which is kind of on the back. Has a radio receiver, which can measure, VLF and such. And has a super thermal electron imager. That kind of didn't last, so I don't know if there's much chance of getting anything off that. But certainly for the 2 events on this, EPOP was going through, now let me actually stop sharing. It went through twice, essentially. So the first time, I'm trying to get some quick look plots here. Sorry, folks. Where is that? All right. This is, hopefully everybody can see this. This is a summary plot for the ion mass spectrometer on EPOP. The thing about EPOP is it's designed to be a campaign type of satellite, so it's not on all the time. So it's on very sporadically. And usually it's on by request. But you can see the track here, and we were right over central Canada starting at 542 UT. So that is just after, I think, that first observation. I made an inquiry into Calgary about interpreting Calgary's the PI institution IRM is PI'd by Andrew Yao, and Andrew Yao is also the mission PI. But I got some interpretation about if there's anything interesting happening, you know, in the spectrometer. And what we do see here is that the spacecraft is going out of eclipse and into eclipse, or sorry, out of eclipse into the sun, essentially, right at about 5:42 to maybe perhaps 5:45 UT, a little bit after 5:45 UT. We do see oxygen and we do see hydrogen, but hydrogen only shows up once we're out of eclipse. There is some flow in the anti-ram direction, which you see here. There's a bit of flow that is field aligned, shown here, but that's about it so far. So the folks at Calgary, specifically Andrew Howarth and Victoria Foss is a graduate student of Andrew Yao's, will be looking at this a bit more in depth. The magnetometer was also running at this time. I asked David Miles to see if there's anything interesting happening here. I think from our experience, there's generally not a huge signature for field line currents with Steve, or it's not really, you know, significant or like, you know, hit you over the head with a hammer kind of huge field line currents. And then it also went through at around 7 UT, I believe, 7:30 UT. Now the mass spectrometer wasn't operating, the mag was operating, and I believe there's a beacon on board, the CERTO beacon, that, you know, emits to ground receivers. It was operating at the time over the North America passes. So I'd have to make a call to Carl Seifring and Paul Bernhardt at the Naval Research Laboratory to see if there's any useful data from that may give us some tomography through the region. So the nice thing is that EPOP was on twice, which is, you know, I with Bea, I ran EPOP every night for, I think, the entire year of 2020, when it was essentially over Saskatchewan between, I don't know, 3 to 8 UT or something like that. And I don't think we caught one Steve event once. So it's hard to catch Steve with EPOP. It's not swarm. That's the moral of the story. But there's some data there we can start digging into and seeing if there's anything interesting.
Sorry, I missed. Did EPOP has some wave observations during this time?
The magnetometer was operating, but not the radio instrument. The radio instrument was not operating. It doesn't operate as often as the other instruments because it's a data hog. It produces a lot of data, and that, you know, takes up all the space. So it wasn't operating at this time, unfortunately.
I'm still glad that there is hope, and maybe we'll get more data, because as you said, we have been hoping to see more EPOP data for Steve. So I'm going to be a little bit out of my comfort zone here, because I did find some Firebird data. I have the data itself that I haven't analyzed, but I have also the summary plots that I'm hoping that someone that understands, understands storms better than I do could help with. So again, this is September. I'm going to highlight 2 to 3 now. And at that time, we do have some activity in the DST index. When I zoom in for, I don't have the DST, I skipped it. When I zoomed in for a couple of days, you can see a decrease in the DST from about minus 25 to minus 50 nanotesla. I talked to a friend who works on radiation belts, and he has been making categories for storms. And this particular one with the DST, he doesn't have it as marked, but the one on the second he did. And I did manage to get data from him for that. For the AL index on the third, it's a very, very active time, and you will see it also in the AE index, but it's more or less in a recovery of what I will call consecutive substorms, or at least injections. When we look at the rest of the indices, I found that Omni didn't have data available at that time. However, what my friend corrected is this is Omni, but Omni 2 had data. So we do have Omni 2 in a couple of extra slides. I told you briefly about Firebird data, and Tomoko asked me about Firebird, and since I'm not a radiation belt person, I knew this could be interesting, but I didn't remember exactly what was Firebird. So for everyone that is like me, not very familiar with the radiation belt, Firebird is Firebird 3 and 4. They're a pair of CubeSats, a 1.5 unit CubeSat by the Montana State University, the University of New Hampshire, and Aerospace. And the mission is to assess the spatial scale and spatial temporal ambiguity of the magnetospheric microbursts in the Van Allen radiation belts. So Firebird is basically a low orbit satellite. There are 2 CubeSats, and they're at an altitude of about 500 kilometers. And this is the data for that event, and I'll go to the other ones later. I have them again. So this is Firebird 3, and this one is Firebird 4. The way the data is plotted is we have mid energy between, it's around 300 keV in the first panel. This is in the Northern Hemisphere, the same energy channel in the third panel, and then the MEV type of precipitation in the second and in the fourth panel. But most importantly, this is courtesy of Victor Pinto. I want to thank him because he was the one that looked at this. And fortunately, Victor has plotted the data for all the Omni 2, and this is the CMH, solar wind speed, solar wind density, AE index, and magnetic field in the Z component. Steve event is slightly wider than this, is 2 and 3 right now, according to what we're talking. According to the decrease in the CMH, Victor marked the beginning of the storm on September 1st. And then the 2 Steve events will be occurring in the recovery phase of the storm. And he has defined the recovery phase in this case as the CMH index has recovered at least 80% from the minimum, comparing this decrease over here from the main phase. So, yes.
Sorry.
Absolutely.
But it's workshop, right?
Yes, absolutely. Please don't let me speak alone.
Okay. Basically, not to concentrate on the recovery phase of the storm, because multiple substorms, and you should
absolutely
follows recovery phase of substorm. So if they are not overlapping, the next expansion not overlaps with the recovery of the previous substorm, then you can get stiff right, every time during each substorm recovery, not just storm recovery.
Absolutely, yes. The reason I'm emphasizing the storm is because when we selected this event, we wanted something that would be slightly different from the DST perspective from the first one. And they ended up being 2 kind of storm-related, very relatively similar type of events.
And also comment here. So, Beat, on this data, Artemis has a good solar wind monitor. So I did look at that for this event.
Do you want to show it?
No, I don't have to, but I could. So just very briefly, and then so this is for the September 3rd the event from 3 to 5 UT or so. So this is the time is B, magnetic field in upstream solar wind. This was somewhat puzzling to me. Bear found that on average time of B wide is weakly negative, but this one was positive B wise. So from the oral point of view, the oral configuration was also different. So there's a clear difference from the 2008 event that Bear has shown earlier. But anyway, the IMF-PZ was mostly negative, so that was probably the driver of this substorm. And there was also fluctuation. So we have this data. If you want to go into detail more than what Omni2 can do.
Yeah, definitely. And the BY is interesting because it's positive, but it's also not small. Every time we have looked at it,
positive. So it goes against the average that you found. So that was very puzzled by seeing this.
This will definitely be interesting to look with the simulation to see if these will produce an even larger asymmetry in the convection pattern.
Yeah, I'd be very curious if Valerie and Tomoko can look at convection, see if there's any differences from the other Steve events.
There shouldn't be kind of instant correlation. There should be some time delay, variation.
Yeah, so I'm kind of looking at that on average trend, not looking at small wiggles. So on other Steve events, I don't mean to steal too much time in here, but so this is
you are allowed to steal time.
Yeah.
Thanks. So this is IMF data for 2008 March 26 to at the end of 20 days. Clearly on average, the IMF-PY was negative for almost throughout this storm. So each one of the steep event happened when the IMF was PY was negative. So in terms of global convection standpoint, that these 2 years of events have are in very different conditions, even though we see similar steep. So that's very puzzling, but something interesting. Yeah.
I'll be curious to see what like the global MHD will show us for injections with.
Yeah, it's a great challenge for global MHD. How can global MHD explain the occurrence of intense SAID, even though the solvent condition is very different?
Yeah. Now, can I ask something? Or so you're looking for the positives, right? So, but we are not focusing on the negatives, meaning similar conditions that are occurring in other days, but there is no steep occurring. Could it be that the similar conditions, I'm talking about, I know BY, as you're mentioning, being positive, but in the slide that you were showing, Bea, you were discussing those indices. The period was from 4 to 6 UT, but then you also show the movie happening at 7 UT, right? So I think sometimes we are missing the bigger picture. And yes, we are finding these correlations or these effects, but we are not seeing the opposite or the complementary information that you have no steep when the BY conditions are completely different to the ones that we see here.
So I have one comment about it, Carlos. I know. So these are the times when Steve was confirmed in the available data, but it doesn't mean that Steve was missing in other times. We simply don't have data when North America is not on the night side. So it's so very hard to know if the Steve is there in other times. But one hint maybe that may be available by just looking at the occurrence of intense SAID.
Right.
So fortunately for this 2008 event, we had 5 DMSP in operation, so we had pretty good coverage of plasma flow measurements in the dusk side. So these are the 5 DMSP satellites. So I made kilogram of the westward flow in the southern hemisphere where the DMSP was crossing the premium night sector. So these the magenta highlights the times when the plasma flow went above 3 kilometers per second. So they includes the Steve observations that we see on this slide. If I just move in here, so middle of the first day, early in the second day, early in the third day. So there's in here, and here. But notice that there are lots of other passes of the MSPs where the intense SAIDs were measured. So if Steve is related to intense SAID, Steve could be happening in other time. We just didn't have appropriate data coverage to measure Steve emission, and they correspond to intense substorms. So the first one was pretty isolated substorm, and a series of substorms started here, then came a little quiet, then the SAID is gone. Another series of substorms came in, then lots of SAIDs happening, a little bit of quiet time, SAID is gone, substorms came back, more SAIDs. Later on, we didn't see SAIDs, even though substorms are happening. So overall, intense SAIDs were happening, and they correspond to an average negative 5 FPY. So that's a potential explanation for the question.
That's beautiful. I mean, are you sure you didn't stitch those data? Like, no, just
no, I can just remove these highlights there. Intense SAID is there.
Okay. Yeah. No, it's true that, for example, if Chris goes, he will not report one night there is no Steve, and it could be that there is a strong SAID, but there is no report of no Steve, right?
That's an interesting question. Yeah, if we have not good image coverage across the US sector, there is absolutely no Steve, but if we see intense SAID, then it's a real challenge to us how to explain the connection between the SAID.
Right. So I would like to ask this question to Chris. What happened, Chris, when you go outside on a night and it's very boring? It's like you call it quits and don't do anything, or you record that night like useless, freezing death, nothing.
No, call it quits. Don't do anything. You're spot on.
From now on, you should register that. Let's add to the list of things to do, because I think that would be,
No, Liz has said the same thing, right? To constantly report the negative observations, and of course we never do, right? Because we're looking for the positives, right? We're looking for the big pretty stuff in the sky, and when there's nothing out there, it's So we can definitely add that to the activity list.
Because what will happen, right? You will be for UT in that sector, and you will report that it was clear that nothing was happening, and Toshi will measure SAIDs 4 kilometers per second, and then we don't know what's happening.
That's a real challenge.
Yeah. Thank you.
We can't always, we definitely can't say anything about the absolute rate of Steves, but just watching the community report, it does seem like, I'm not going to say 100% of them, but a whole lot of them are reported around the world because people are now watching out for them and, talking about them one way or another. So that's one of the reasons why Michael's database has so many more events than the FEMIS number of events that have been seen. And that's a sort of separate question from looking at the this set of a few days that has a whole bunch of Steves. It's a related question, but I think from, I think the main idea, and correct me if I'm wrong, Bea, but the main idea was we have a whole lot of system observatory data for this couple of days in March of 2008. And so, you can really do a case study of kind of putting together a whole bunch of different data. And I also wanted to ask what the plans are for sort of sharing some of these plots and even further continuing discussions. Bea, I also know that you and I and Burju looked at a number of events, and these were a couple of them. So
absolutely,
we also have us like 3.5 years ago. So I found that file, and you know, we also have some of the ground-based magnetometer data, some geotail data, some LANL data, some THEMIS data, you know. So I don't know if I'm happy to put those somewhere, but I wasn't sure what the plans were.
I agree, and this is an excellent question. We actually were talking among the organizers yesterday and collecting all the slides and sharing that with the people that is attending. I think is going to be very important, so everyone can kind of grab data, and we'll probably have to set up something. I'm not sure if we agree on what platform we will use.
Yeah, we're working on that. Yeah.
And about the previous work that we did together, at least we should go back to that.
I have a general question, Toshi, Bea. It's related to the length of the substorms and the length of Steves. So has anyone looked at, let's say, the typical or a 45-minute Steve observation, 30-minute Steve observation is related to a substorm, or the recovery phase is only 15 minutes or 30 minutes, or some kind of correlation has been done?
There is a paper by Gallardo Lacour et al. In 2018 that looked at substorms and Steve, and what we did there was, and it might not be exactly what you are asking for, because for that we will need to look at every single one in a separate way. But what we found is that usually Steve occur during an interval of the recovery phase. So the recovery phase is usually long, and the expansion phase is usually long. So typical expansion phases, when we compare it with the SuperMag database, typical expansion phases from the 16,000 substorms that we analyzed was about half an hour. For the Steve events, the typical expansion phase was an hour. And that is from the magnetotail and all the injection part. It's really important because it's really, this is something that Toshi also talked, is the magnetosphere kind of modifying and giving energy to the system. But the recovery phase is long.
Right. Okay. So it's focusing on that particular event, September 27, 2017, that some conditions or some characteristics were such that, yes, that's a long-lived Steve, and end of the story. And so we'll see.
And I agree, when I was classifying that particular Steve event, I remember talking to all the collaborators and saying, is this a Steve? I have never seen a Steve that is this wide, and I have never seen a Steve that is this long lasting. It's both of those parameters are the largest in the whole database that we had. But one thing is interesting, and one thing that I always like to highlight, and please, Toshi, correct me if I'm wrong, when we look at the aurora, especially when we look at the two-dimensional time sequence, Steve looks fundamentally different than the regular aurora. It's so different that when we were looking at the first observations that Toshi and I made, we saved that data in a separate folder because it didn't look like anything we have looked before. And talking to Eric Donovan on this, he also had the same impression. So we are able to distinguish Steve from the white light, but we completely needed the citizen scientist data to know that what we were looking was a physically different phenomena.
Yeah, I agree with what you said there. I clearly remember the first moment when you showed me the very first event of Steve. So in white light, it's very clear it is the strange kind of emission in white light that doesn't look like anything we're familiar with in a permanent night sacral or oval. There is no discrete or near equal boundary. in white light, we can make that sort of judgment. As now we understand we're looking at the continuum emission. The problem with that September 2017 event is that is seen in the red line data. So there is no other data source. Like you mentioned, it's a broad, long-lasting emission. When you showed me, my first reaction was, yeah, it could be Steve. But when Carlos challenged, I became unsure if that's still Steve or Sark, because there's no other way to prove that this is a Sark or not. So that is still a challenge that we have. If we have limited amount of information, how can we be sure whether that's Steve or not? But yeah, you are right. There's white light, then yeah, that's a good solution.
I think Bea was experiencing Calgary fever for Steve, and yes, let's call it Steve. Sorry. Please go ahead.
Basically, it's qualitatively easy to understand why Steve appears during the recovery phase. Because during expansion phase, the particle population near the boundary, auroral and subaraural boundary, as I try to convey, is kind of, there is overlap between the particles in the plasma sheet and inside. Overlap in sense of suprathermal particles. Okay, so you have kind of, it's very difficult to distinguish between bright light from auroral precipitation and almost the same bright light from suprathermal particles precipitation, which are about half keV, 200 eV, etc., etc. Then, when during recovery, you have a splitting, basically, so that you have clear boundary between auroral and subauroral stuff. And then it's easy to distinguish. And by the way, regarding concerning Steve, it's you need a significant N2 population in this region to get continuum. So to get N2 excited, and that's a source of continuum for the Steve. So it takes time also for uplifting the atmosphere.
I have a few plots regarding the relation between Steve and recovery phase. So can I share those?
Absolutely.
It's not a presentation, just showing some data to everyone here. So this would, we already saw this, March 26 event where the Steve duration is nicely consistent with the duration of recovery phase. But other events were somewhat different, and that may be interesting to look at. So it's a similar style of format, but for March 27 event, the MFPZ was south, like Bear mentioned. The storm was going on. The substorm was somewhat complicated. The first substorm occurred here, then there was a secondary intensification going on that can be clearly seen in the kilogram in one of the images in here, and that marked the initiation of the Steve. So this is the equatorial boundary of the oval. The Steve started and Steve ended in here. The end time may be close to the end time of the substorm, but most of this Steve was within the somewhat steady convection for 30-40 minutes. So it was not a classical recovery phase, but Steve was going on. So this one was somewhat different from the classical type. And this was, by the way, nicely associated with a big oral intensification or the streamer. Then the faint Steve appeared in here, then it became more pronounced later on. So there's again the strong oral intensification associated with Steve. Just the relation to the recovery phase was a little different. The 28th event is even more puzzling. So there are multiple intensifications of the oral electrojet going on. Again, negative BC, negative BY. The Steve was somewhat recovering in this time period. That's somewhat strange. The initiation of Steve, I should draw another vertical line, is here. So that coincides with one of the secondary oral intensifications. So that's probably this one. So Steve was not starting with the earlier one, or the later one. They don't appear to make any modification of Steve, but Steve was already going on when the AE was still high. Then the recovery phase was probably here, then the Steve decayed. So even when the AE is still high, the Steve can appear in association with one of the intensifications. So, so it's not like the Steve is always associated with the recovery phase, but it can happen during the steady convection. The last one on the same day was a nicer one. This one happened during the recovery phase when the secondary intensification happened near the end of the expansion phase. It took some time until the effect propagated down. You can sort of see some diffuse stuff propagating down. That probably indicates some particle injections coming from higher L shell to lower L shell, not probably the plasma pulses around here. So that turned on Steve, and it died when the substorm died. So even though these 4 events happened within 3 days, in terms of relation to substorms, each one of them shows somewhat different signatures. The only thing I see in common is the secondary intensification. Sometime during the expansion phase, when near the end of the expansion phase, that turns on Steve, and then it doesn't matter too much whether the following activity was strong or there was no following activity, and then the Steve dies eventually when the substorm activity ends.
So Toshi, how do you relate these kind of observations in which you have Steve appearing during the secondary intensification with your results that show that Steve occurs when the injection is happening away from the midnight and closer to 21 MLT? So it's like you have a boundary 21 MLT plus or minus. Sorry, I didn't read the paper, so maybe it's there. But could it be that you have the Steve appearing during this secondary intensification because you are closer to that sweet spot for the efficient timing, or not necessarily?
Well, I think that is the case. So these are snapshots. This day has pretty good sky measure coverage. Steve is appearing in here. This is the start. This is the maximum Steve extent. So this is a midnight, so it's around 21 hour local time, and that coincides with the intense oral intensification that happened just before the Steve emergence. So early on, the aurora was a little bit closer to midnight, and this one expanded over to Alaska, and then Steve started to appear in the Alaska meridian. So we still see the same relation between oral intensification and Steve occurrence. So probably when earlier intensification happens in later local time, so the injection was not suitable for creating Steve, but we do need a secondary intensification to initiate the Steve.
Okay, thank you.
About the SMC, I have a comment and a question. That's an interesting point because that's something I also noticed in the AL index, and I reached out to Anna de Jong, and she has a list of events from the global perspective of SMC intervals. And I know that some of these Steve events actually occur during SMC, and that's an ongoing work that I'll keep you informed on that. And about the AL index, this is something that we also talk with Tomoko and Valerie, that the expansion phase is not that often, and I don't know how to describe it in a better way, but the AL index, you see a decrease, and it's not like the classical decrease in the AL index where it's one sharp decrease, but it can be like a multiple step type of decrease.
Right.
And that is not that uncommon to see for this type of substance either.
Yeah, so these are, it's not really a storm, but relatively strong driving -5 now Tesla with BZ. So yeah, you are right. The initial decrease is not an expansion phase. That's the growth phase or oval was moving equatorward until this time. So this little drop is actually the expansion phase. So it does look very different from the classical non-storm time substorms. And then, like you said, there are multiple secondary intensifications, one of which started the steep down here. Yeah, so there is something special going on in this storm time, or strong driver creating enhanced auroral electrojets.
So yeah, back to the very initial question the Bayer raised at the beginning of the session. So we're talking about many about what turns on the Steve. So what process do you guys think turns off Steve? So and the related question, is there any kind of a specific study on the typical time scale? I mean the lifespan time span of Steve events from either the scientific camera or from the citizen scientists the data. So that's very important. Trust me, I think a lot. What's the kind of how long it will typically last, and what's the shortest time scale, and what's the longest time scale you have seen?
The shortest I have seen in Themis ASI was 15 minutes.
Yeah, but in this, as I noticed, in this kind of the Canada the Thanksgiving storm, the Steve appears in 1.5 minutes. So some very lucky people actually catch that.
Oh, that's super quick.
So yeah, that's another question bothers me, because that will obviously affect our interpretation of the Steve emissions. So yeah, I wonder if somebody can take some sort of the specific look into this.
One of the things that I wonder is in one of the papers that we have with Alan, where we show some images, combine the images, if it is possible to not predict, but look at conditions that might indicate that a buildup of ideal conditions for exciting the optical emissions are occurring. So specifically, I had shown there were signatures in DMSP satellite that were related to SAID or large SAPs and enhancement in temperature, but there was no optical signature. Later, it was a different satellite or different paths. Similar conditions were there, and you could see Steve. So the question is a build-up necessary in order to have Steve, or as John is saying, you see one minute long structure and that's it. It's like a very spontaneous, direct, and gone.
Yeah, I have my speculation. It has something to do with the neutral conditions there, but unfortunately, the neutral observation is very scarce. So the key altitude of interest is very scarce at the moment.
You know, guys, you forget maybe about some hidden factor, and that's a neutral density. And the neutral density, as we believe at least, is the key for the stiff spectrum, continuous spectrum. Okay, so you need time to uplift the N2, uplift nitrogen to the stiff, altitude. And it's usually even for the strong driver. And that's simulations done back in 90s by the UK group, where Fuller came from. Takes about at least 10 minutes if you drive like 5 kilometers per second, electric field. Oh, sorry, I mean, you understand. That's one factor. If you have a weak driver at the beginning, for example, when the dip is not formed deep enough, and so the electric field is not increasing enough, then you don't have stiff. So that's a factor which should be somehow measured. And I think if you say, I mean, there is technique to measure, neutral density, right? And Champ, for example, I think it still was working at that time in 2008, right? Or timed, for example, timed satellite. So it should be, I think, good addition to look at that.
That's a good point, because time is available. I didn't look at the data, but time is available in one of the events. I think it's the second one. And we did try to look at Gochi data that also will give us information about the neutrals.
Yeah, Gochi is excellent.
The conjunctions with the list of events that we had was not successful at finding anything useful.
I forget I mean, the twin satellites. I forgot the name. I used the data, but forgot.
Well, actually, Julian and I also tried to find some, Champ, Gochi, and Grace conjunctions, but unfortunately, we don't find anything useful. There were a few conjunctions, but we didn't see any,
but that's not the altitude. Basically, that's the problem here. That's not the altitude we want.
Yeah, so there could be altitude problem, or could be timing or anything else, but at least
and the latitude and the resolution is not great for the latitude. We need a very high latitude resolution to resolve that structure.
Yeah.
Molecular diffusion is pretty quick, though. So I would imagine if you measured a neutral enhancement up at 400 kilometers, that would still be useful to determine what's happening down in the heating region.
Yeah, that was our initial hope. Just, within the data resolution, we didn't see any significant neutral density enhancements.
I've been working with some researchers at the European Space Agency, trying desperately to get useful information out of the accelerometers on the swarm satellites. On the few events I've currently been looking at, they haven't had any. The data just looks like garbage, and they can't do anything with it. But it might be worth expanding. If we got a larger expanded coincident event list, we might get lucky.
Yeah, actually, myself independently, I also looked into the swarm, the accelerated data myself, and that's not quite useful. Yeah, there's some kind of instrumental issues, and the resolution is not great.
Yeah, Swarm C appears to be the only one.
Yeah, only Swarm C has some sort of the reasonable data, but yes.
Even then, very hit and miss.
Yeah.
One thing that I noticed, how can this be tangled to this altitude dependence? It seems that if you happen to have some common observations from DMSP and swarm, the elevated temperature measured by swarm usually is higher. So you could argue that that's an instrumental offset or bias that measure higher temperatures, but also brings a question, I think we discussed this briefly with Toshi at some point, that could be perhaps evidence that at 850 kilometers, you are seeing only effects of, as Naomi was showing, this heat conduction. And when you get down to 400 kilometers, there is some of that plus whatever heating is being created by these neutral ion drag mechanisms. So it's natural, or it should be natural, to have swarm measuring higher temperatures. So I don't think there has been any kind of analysis or statistical study showing this as a consistent difference. And if something can be said that if DMSP measures similar velocity, similar temperatures and swarm, what are the implications? That you don't have strong heat conduction and it's basically everything ion drag, or what?
Yeah, that's an interesting point. And especially if we're looking at, if we limit ourselves to electron temperature measurements, all three swarm satellites would be able to measure that reasonably to compare to DMSP.
Mm-hmm. Seems we're all tired. No more ideas.
This is, in case anybody's noticed, this is very much an open discussion time frame in the schedule. So it's not shocking to have maybe lulls in the conversation.
One thing that I'm not sure if we have analyzed, and that was clear in Toshi's kilograms and several other kilograms, is we do see Steve moving, especially at the beginning of the observation, pretty quick equatorward. Have anyone done anything to understand that motion?
You can basically, if you relate, I just stick to same scenario. If you identify the separatrix, right, subaraural, auroral, to the plasma pulse, then it's, I mean, okay, I don't want to be too old, man. It is known that plasma pause moves inward, right? There are two effects. First, of course, convection moves it. Increased convection, you move it. Second, SID itself. Erosion, plasma pause erosion means that you get new boundary in about 5 minutes. If you have a huge electric field, radial electric field at the plasma. Understand? So that you have standard drift trajectories disturbed, and plasma, cold plasma, initially being trapped, now becomes untrapped. And so it's lost. And the lost time is about 5-10 minutes. So that every 5-10 minutes, you have plasma pulse moving inward or equatorward in the ionosphere. And that explains so continuous motion, gradual motion, equatorward. Now, given that the conditions, I mean, still you have hot plasma coming in.
Does anyone have on the top of their head the speed of that equatorward motion?
question. I remember we
Yeah.
calculated it.
I mean,
You remember, we did it.
I did that for a number of events, but I forgot. It's probably a couple of 100 meters per second, some sort of like that.
Yep.
That's,
From 200 to 400, that was like a fast thing. That was something that caught my attention because for SAR arcs, that's kind of fast. SAR arcs usually go around 100, no more than 200. And depends a lot on the kind of activity, the type of activity you have. Sometimes you can see the arc moving gradually, and sometimes you see briefly, like moving very fast, slows down, and then fast again. And that coincides with like injections or big pulses. But I never seen 400 meters or 300 meters per second in SAR arcs.
It's simple estimate. If you take, for example, dimension like a stiff 1 degree, 100 kilometers, and characteristic time is 10 minutes to make erosion, right? So you'll get 1/6, so 160 meters per second. Kind of ballpark estimate. So 100 meters sounds reasonable for erosion.
Yeah, I was just thinking, I mean, if that could help constrain any of the photochemistry, because we've been talking about the structures that go sideways, but when it moves equatorward, it should, maybe leave a trail behind, so to speak, depending on the mission lifetime. But if we say Steve is 5 kilometers thick, just roughly 100.
But it's westward, right?
I thought we were talking about this is moving southward or equatorward.
Equatorward, it's 100 meters per second.
Yeah, so that would mean that it would move its entire width in maybe, I don't know, tens of seconds.
10 minutes.
10 minutes. Okay, so probably too long.
And it's the same order of magnitude you need to pump, vibrational level.
Yeah.
Yeah, just to correct to Brian, if this motion, I mean, a couple of 100 meters per second is together with the neutral wind, then you will not have trail. You will not have trail.
Right. Yeah. There's the same order.
It's just exactly, for example, it's just exactly the same as the neutral wind motion. Then the trees will just move with this the motion.
Right. It's the difference between the apparent motion.
Yeah, motion and the neutral wind speed. So that's why I say the neutral observation is the missing link there.
Yeah.
That's true.
So what is a typical order of magnitude or value of the neutral wind at several regions? I mean, 200 meters per second seems fast, but I'm thinking equatorial region, right? So it's completely different condition. I know in the Aurora region that is even faster, but it's 200 meters meridional wind is something okay, or do we know?
I was just trying, there was a paper that came out recently of FPI measurements during substorms. So I was trying to find it, but off the top of my head, I would say that's not unreasonable.
Okay, yeah, thinking I should know this, know that we have an FPI here in Milton here, so.
Yeah, I think that paper is written by me. I think you referred to that. Okay, yeah.
Great paper.
Yeah, it's a bit high. Yeah, I don't think that for the FPI that the equator motion, the westward the neutral wind usually typically reach a few hundred meters per second. That's typical. For the equator part, it's barely reached 100. Something reached 100 meters per second for the equator wind. But it does what we observe. We have seen it does intensify during the steep time. Yeah, the equator wind.
That's consistent with the study you did with Ying, right? Just to remember. June.
Yeah, I think you're right. Yeah, I'm just taking my coffee.
Why don't you put the link? Why don't you put the link on the website, on the chat, so we can take a look.
Okay. So, okay, I can do that.
Yeah. So I see Chris, Alan, Emma. I don't know if you guys have any question, comments. We've been talking a lot about indices and satellite data, and so I don't know if you want to add anything to the discussion.
I've just sort of been lurking and listening as you guys have been talking about indices and
The discussion is way over my league, I'd say.
yeah.
I meant to ask you yesterday, guys, to the citizen scientists, is there something that the scientific community can contribute to help the work that observers do?
Well, Alan here. I think I'd like to see. Doesn't necessarily help us take better pictures to give to you folks, but I'd sure like to know better what it is we're seeing and photographing as some sort of new atlas of auroral forms developed. The ones that I see published are decades old from the International Geophysical Year. And now with the digital cameras, we're seeing through our cameras many more forms than anybody ever saw before. Things like the SAR arcs we never see them with our eyes, but the cameras pick them up easily. And these green blobs and all that. And it'd be nice to have some sort of photographic atlas of auroral forms that we could turn to and say, well, that's probably that kind of formation that we saw that night. Or, but it certainly attending this conference, it certainly sounds like there's a continuum of forms. So it's really hard to pigeonhole all these different subaraural arcs and forms and anomalous arcs. But nevertheless, some sort of atlas of auroral forms would be great to be able to refer to.
Hi, Alan. I'm Megan. Hi, I'm from the UC.
Hi, Megan.
We actually are kind of doing a little bit of that with the Aurora X project, and we have something called the Auroral Zone, which has some of those sort of definitions already, and that was a sort of precursor to some of the stuff that we are doing, where people who are not particularly familiar can go and look at arcs, see what they want for diffuse aurora, see what pulsation aurora will look like, and stuff like that. So I encourage you to check that out as a starting point. And then, yeah, this is a great idea to like add to what we're doing, or what Eric and such are doing with the Aurora X project under the documentation and stuff, to give people an idea of what type is what, and like a little blurb on what we do know about formation of some of them.
So that's inside the Aurora X website. There will be a box for forms or types of aurora.
I hope so. And if not, then it's something to definitely bring up with Eric to include.
Yeah.
If it isn't already in their planning. Like I do know, like with the Auroral Zone project, that one was centered around giving people exposure to different types of auroral forms. Not Steve at the time, this was done a couple of years ago, but there were documentations of this is what an arc looks like. This is what diffuse aurora looks like. This is what an omega band looks like. And that project actually was fantastic when it let people help classify the data. And so it would train you to see what an arc was, or what an omega band was, or various types of auroral forms, and give you a little bit of information about it. And continuing that on with the newer stuff in the last, I want to say about 4 years or so, would be fantastic. Like things like the dunes look like. Steve's not in that one yet. Even things like beads, arcs, the stuff from Thanksgiving that I have no idea, the candy cane things, like all of these things are new and we haven't caught up with them yet. So I'm really hoping that this will be how it goes. And like there is that section in the Aurora X site for the citizen science images, and this would be where this would be fantastic, so that people will be able to know more, because it's awesome.
That'd be terrific. I've not looked at the Aurora X site yet, so that sounds like a great place to put that kind of atlas, and we'll check that out, and we'll be able to refer our fellow citizen scientists to it once we get the.
If you go onto that Aurora X site, there is a citizen science like area, and I think the link to the Aurora Zone is there, just to give you a feel of what I was kind of talking about with, and like there's a tutorial in the thing where basically it shows you, it's very like rudimentary, but I mean it does show you some information about certain types of things that were like 4 or 5 years ago.
Yeah, I think that's all in there, Megan. I'm just looking at it right now.
Oh, good. See.
It also makes me excited that you're mentioning it, because my daughter was working as a summer student with Eric on Aurora X this summer, so it's nice to see the circle come together.
Yeah, it's going to be amazing. Like it's a super helpful site for any, like the whole span of people wanting to look at Aurora. There's something there for everyone. Like I could put my 12-year-old and she could have fun on the site too, right? Oh, yay. So this is what I was kind of thinking.
Yeah. I was going to ask Megan, for the descriptions and sort of photographs where you're outlining all the different types of aurora, are all the example photos from scientific instruments like this?
Yeah. So when we were originally doing this, that's what we had.
Right. I think
this would be an amazing opportunity to update that, because like I love our cameras, but we trade off from sheer beauty for more qualitative study, and it's like, you really
the Alberta Aurora cases probably have
and also
way lovelier pictures of all of these than we do, and so working with them to get some like really stellar examples would be
and like remember, like things will look differently with respect to different perspective changes. So when you have what I would call a traditional camera versus our all sky imagers, you're going to get different looking things with the same features. So like if I'm up looking at something and it looks like arc structure, it will look differently than it will in my all sky camera, where you can see the segmented arc structure moving through. It'll be more overlapping depending on angle and distance, and different perspectives are vital, right? Like, so, and this is where having access to the citizen science, like it's valuable.
Yeah, I think Eric tomorrow will talk about Aurora X and citizen science or something, right, Bea?
Yeah, he's talking in the second session tomorrow, and we should definitely ask him exactly what Alan asked, if they're planning to do some catalog that you guys can use, because I think that's also an excellent way to an excellent path for discovering new things. The fact that you guys will know that this has not been classified, so you can go back and say, hey, we found this and it's not in your catalog. How do we call it? What is it?
Yeah,
so I think
that's definitely something to bring up with Eric tomorrow, because there should be adding to his feature list an upload of what is this, and then people can look at it, discuss it from everywhere, and go, we think it's this, or add to tomorrow's I don't know section.
And this is a great place just to suggest or try, if we discover something or someone discovers something, let's come up with a nicer or different name. Then let's don't call it Joe, okay?
Because are we calling it Carlos?
No. Oh, look at that beautiful Bea. No.
I'm sorry.
I love the name.
No, just joking.
I think we would find that when we start to contribute pictures of all these different events, and especially as we get solar maximum peaking in the next few years, we're going to find more of this continuum of we'll submit pictures, and well, it's not that, and it's not that, it's sort of both.
So yes, we will have.
We're going to begin to see this continuum of forms, I would assume, and how, as we saw in the beautiful video yesterday, how one can evolve into another. And I think that's our priority as citizen scientists: get you more data over a longer period of time, over a night or an evening, to show that evolution. not just a few seconds worth, but hours of time lapse or real-time movies that we can do now. You can see the whole evolution, because what I learned from a week ago Monday was, even if you can't see anything, shoot, because there can be these red arcs there and they could evolve into something else that, just keep the camera going, because something could happen. That is great to document how it started to form.
Yeah.
Alan, if I could continue on your very excellent point as well, I just wanted to mention for the scientists, we really desperately need to update our terms in terms of getting you, useful information. So like those ring things that we're seeing on the Canadian Thanksgiving, I am staring at my iPad in front of me right now, reading a thesis, Hannah Dahlgren's thesis from 2010, and looking at the, citations in there for auroral folds. And Toshi mentioned that earlier, that might be a fold or a curl or Kelvin-Helmholtz. There's so many different things it could be, but there is quite a bit of past research on all of this. And, your suggestion to me also kind of gave the idea of kind of more like a family tree with some provenance for what these terms are or how they're related would also be really excellent.
Yes, that's right. There's a lot of terms that we hear from your community of these various subaraural forms and the like, and which have developed over the decades because they were observed this technique or that technique. And now we're realizing they have visual manifestations, perhaps, that we're calling something else, but it's really just a visual manifestation of something that you've been talking about, that you've observed just through infrared or radio or whatever it might have been in the past. And it's because of all these digital cameras that we can pick up this stuff. And there's just so many more people out there shooting that.
It's also really hard, even the substorm and storm terminology is difficult because substorms look different during storms, and scaffolding all of that out is a really good challenge. That's why you guys are capturing things that haven't been described, or they've kind of been described, but they were, in papers from Alaska 30 years ago and different cameras, and we're kind of working together on that. So it's excellent.
That's a great point about the terminology, because it's challenging to enter the field even as a student when all the terminology is there and you have to learn it super fast, even now. And that's the reason we created the glossary that we are going to give you at the end, hopefully more completed. But I just remember that, for example, when you talk about different substorms and storm time substorms, Toshi and I were talking about SMCs, and we never describe what an SMC is. So that's going to the glossary just for general context.
And something to mention is that if you are not in the field, in the magnetospheric field, you don't even know those terms. So it's not unusual to have people not understanding terms that are specifically related to a given area, even though we are on the same large field of space physics, if you want. Many magnetospheric terms for me are like, oh, what is that? Need to recover indices and descriptions. That's something that happens everywhere.
Even when you are in the field, like today I learned about auroral hems, and I had no idea what the auroral hem was. I'm like, what on earth is that? Like what Benji was saying. And it was like, I need to look up what an auroral hem is. This is fantastic. This is neat, but I don't know what this is. Like, I've never heard this term before.
Megan, it means you are too young.
But still, I need to know this because it seems very relevant. And it's like, I never heard of it. So
Jenny, you know all the terms, right?
No.
You have experience.
Yeah.
I wanted to comment, at least, well, first off on terminology, at least we're not as bad off as I feel as the waves community in space physics, whose terms like hiss and roar and chorus refer to auditory terms, but they look at them visually. That's another ball of yarn. I just had a general question, since, we're in this kind of, based off of what Alan had mentioned earlier, just keep the camera rolling. I mean, this may have come up before, and I'm a bit of a Luddite with auroral photography, or just photography in general, but are we at the stage where the citizen science, the amateur photographers, their equipment for, your Chris Ratz labs and so on, that just far outpaces what's deployed or available scientifically? Are we at that stage?
Oh, I would think so, because our sensor is much larger. Looking at the specs yesterday for your all-sky cameras and the like, you were saying 500 by 500 pixels was a big sensor. Oh, I'm sorry. We've got 8,000 by 5,000 pixels. And lenses
you were
which
laughing.
cover the whole sky. But we're not shooting all night long every clear night. That's the difference. You're getting the data. We're getting it now and then when we decide to go out and shoot for an hour or so. And
now the question is, why
some of
not?
the differences between this is we have CC cool cameras that we've dropped to -65, and there's this is where those trade-offs come in, and the resolution that you're able to do, we at this point I don't believe we can. And then a high resolution image that I see from the chasers, it's wow, it's so exciting, and we won't pick that up with ours.
A practical question related to this. So if I were to tell you, Alan or Chris, just leave your camera on from 1 hour after sunset to 1 hour before sunset, what would be the space and the cost? I mean, the feasibility, or what would be the constraints to say, no, that's impossible to do, or yeah, we can do it, but.
Well, depends on how many, the cadence of your pictures. Obviously, if you're taking one every couple of seconds, like Chris was saying, exposure times are only 2 or 3 seconds. If you want that kind of time resolution, and we're taking that many, well, do the math on how many pictures is that going to be, and they're all 20 to 50 megabytes. You can. The cards are relatively cheap, and you can got 2 cards in a camera, so you could go all night probably and fill up the cards with hundreds, a couple of thousand frames. It's certainly possible. The question would be powering the camera, keeping the camera powered for all, especially in wintertime. And so monitoring that, or having an outboard power supply, but it's possible with the kind of cameras we have to do that, keep it going, and just watching over it and making sure, keeping the frost off the lenses. We don't have them underneath little heated bubbles and plexiglass domes. Keeping the frost off the lenses is going to be the more major problem on many nights, especially in wintertime. So, but it's possible to do, but it takes a very dedicated effort to do it. That's for certain. But from what I saw on the Thanksgiving Day one, boy, if I just kept my camera going, I would have captured much more that I saw from the snippets from other people. So I could have caught the whole continuum of events if I'd kept it going and not said, oh, it's gone, it's settled down, I'm going to go to bed. No, it was going to act up again and give us even more and show us more in that subaraural zone, one thing evolving into another. That would have been a great record. So,
some of what I'm thinking about though on that idea of leaving the camera out, there's logistics too, just in terms of where you put the camera. Like Alan, you're in a pretty dark spot where you live. Myself, if I were to leave a camera out all night, it'd be all urban lighting. Because it's not in a place where I could trust to leave it out. This is several $1,000s of gear, so it would have to be. It's not insurmountable, right? Because it's just a matter of forming a relationship with the right property owner just outside of the city and setting up that relationship. So it's not insurmountable problems, but there are logistics to it too.
Yeah.
Another kind of point, Carlos, is that, you know, people have their own motivation. And so you're asking them to do something that costs money and they're expending their own money for. I would say just kind of on this, there's auroral photographers, and also the previous point, have all kinds of innovation, agility, they can adapt, they can have the latest cameras, and they can experiment with different filters, and all of that is super exciting in terms of capturing new kinds of things. I'm also aware of several citizen scientists initiated projects that are more in this agile automated camera space where it's a COTS camera and it's less expensive. I can give you one link for the cameras in North Dakota that are an undergraduate student department type of budget collaboration and how that has happened. And then also Jeremy Kuzub has his new project. He's going to be reporting on this at AGU. It's a portable auroral imager in a Pelican box. It's fantastic looking. And I think the Personal Space Weather Project folks, Nathaniel Purcell, they may have something along those lines as well as people in Norway and other places have definitely explored these realms.
Yeah, definitely. I think that the aspect that you're mentioning is that the personal experience of going out and doing this is not replaceable. By no means I was thinking that by doing this automatization, you guys will stay at home and don't do anything. But looking at the beauty of the things that you guys are showing, it's really too bad not being able to see more. You know, that's why if you, Chris, bring a good point. So in order to do this, yeah, you need to be at the right place, not in the city. And so you will not be able to populate all the places, but I don't know. In addition to your own experience or the group of guys going out and taking pictures and playing with different parameters, this could be something that is there, you know.
One
You know
thing
what would
that
be interesting? Thinking about it as a two-way conversation, right? If someone from like the U of C or someone watching, I mean, you guys usually look at it after the fact, right? But if someone were to say, hey, maybe you guys should go out and take a picture tonight. You know, there's so, if you know, June were to say, there's something looking weird, or I don't know what's going on right now. Can you guys go take a picture? That would be spectacular. And I know that you're not necessarily looking at it ahead of time. A lot of times you guys are looking the next day after, but that would be super handy.
One thing
that on missions.
I get the impression that you guys often have your finger on the pulse better than we do.
Yeah, exactly.
I was gonna say that usually, like I watch the Auroral Chasers stream like every night, and I'm like, guys, yeah, I'm like in bed asleep, and you guys are like, we're going, and I'm like.
Well, our friends in Manitoba, the Manitoba Aurora hunters, chasers, or whatever, they give us a heads up. I mean, I get a message, comes up and says, we're seeing Steve, and it isn't quite
it's going,
dark yet
it's going.
here. So we're there seeing Steve. So look for it in a couple hours, and we do. Yeah, we head out and we see Steve.
I find what you're doing, you guys have this down. Like,
could we go further eastward then and ask Emma when she's seeing the aurora in Finland, and then could that be a?
We do that sometimes too, right? Well, I mean, we'll watch as far east as we can. Unfortunately, it's a little bit disappointing when you look too far east because, Emma will be out shooting and be getting amazing photos, and then aurora dies off by the time it makes its way across the ocean. You're like,
Yeah, and I'm not sure, and you probably aren't sure is exactly the longitudinal extent of Steve in terms of if he is over Manitoba, are we going to see him over here? There was one night where they saw it early, and we saw another Steve later on that night, and so there's no guarantee that once it gets dark here, we're going to see the same Steve that they're seeing as well.
Back in March, Alan, I think we did.
Okay, Chris, hold on. I think Emma, she's trying to say a few words. Go ahead, Emma.
Yeah, because there's another side of my hobby, and it's the fireball guys and girls. And we do have cameras at tops of roofs, basically. So something that could benefit this community is building or structurizing some kind of prototype constructions based on Raspberry Pi or other these kinds of miniature computers, and we don't basically need to store all the data. Just one night's buffer is enough to kind of go back in time. So that's something that can fit into anybody's computer, even my phone's card or whatever. 1 gigabyte is hugely more than needed for that kind of solutions. And the current cameras for these kinds of miniature computers are quite okay, I'd say, for this purpose.
But it's also in the very wide angle, like fisheye lenses. We also want to get, from what I'm hearing, as much resolution as we can to see these fine structures, see the motion. And so that's the thing, is we have to have the wide field of view, but also lots of pixels and lots of resolution, and in order to see these structures with enough detail to really make something of the data. Or as I can see us needing to do is shoot whenever we're out there and we know we're going to have a good chance of catching a Steve, shoot with the fisheye lens to get the big picture, but then have a second camera ready with very fast, narrow angle to move around to catch, as you saw with Chris's, a snippet, a time lapse of just very fine structure in an area of Steve where Steve is acting up and there's fine motion, to get that with even more detail and structure. And that takes moving it around, moving the camera around, pointing it to where Steve's doing something interesting and doing a movie or a time lapse. And that takes a person there and with a longer focal length lens to do that.
Go ahead. I interrupt you, so you can go ahead.
Oh, sorry. Concerning the question of the longitudinal extent, it's usually, for typical SID event, it's about 2 hours of local time. So 2 hours means that you have about 30 degrees.
Right.
1 hour is 15 degrees.
Right.
Oh, so it's about 2,000 kilometers, if you want.
Yeah.
Go ahead, Phil.
I was going to say, this discussion reminds me of a couple of things that we've also learned in the community of running things like the antenna behind me. There used to be a radar in Sonderstrom in the western fjord of Greenland that did incoherent scatter radar. And when they first built it, they had a joystick. And so when the aurora would appear overhead, the operator could use the joystick. They disconnected it and threw it away because human lag time is always behind where the arc was. What you ended up with often, if that was the only data you had, was a jumbled mess where, oh, I'm looking over here and I'm looking over there. So what Alan said about synoptic, something that's just click, 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 clicking away where you don't have to move it, and then you're free to do something else where you can focus, okay? You're going to get some of the dynamics with the fixed one that you don't have to worry about, did I track it or not? And then the other one, you're going to be able to track some of the interesting larger features. That's a good combination that we've found that works pretty well when you can have 2 different instruments that observe, one synoptic always there, and then one where you're following. So it sounds exactly like the discussion that just happened. So these two communities kind of have similar sorts of operating practices that you can arrive at, and I think that's very good. There was also a debate in the radio astronomy community, or even in our ionospheric community, about if you make all these instruments remote, it's what Carlos said, nobody has to go there anymore, and that's actually very bad for building community. One of the things you have to do is every so often you have to get a student to get their hands on this hardware. And that's what cements it. So the fact that you're going out and using equipment in the field is a big part, I think, of what keeps the community going. And so there is a place for remote stuff, but there's also a place for I'm going out there, right? And I imagine that that's what keeps the community alive, right? Is the, hey, I might catch it. And I think you're all about that. So that's actually, again, it's resonating in different communities. We've just all approached it from different time frames. So it sounds very familiar to me.
I was just going to speak.
Sorry. Continue, William, please.
Okay. Oh, yeah. I was just, very briefly. I wanted to, comment that if somebody has something very specific, like a very specific idea, and they, approach the community and say, "Oh, if we could really capture this, that would be great." Sure. But I think more than anything, I encourage the photographers to do what you're doing and do what you love, because you guys being passionate about it is the only reason why any of this works. And so, if you have great time, if you know exactly where you were and you have accurate timestamps on your camera, I mean, I'm never going to complain.
Yeah, don't let us stuffy ivory tower academic types tell you what to do and where to go. The one thing I think I always tell people about Steve, the whole saga of Steve, that is teaching me, at least as an academic, is that auroral physicists don't go outside enough, and we're too biased by our instruments. So right now it's 8 to 9 Eastern time. So and we're in the stage of, well, our agenda tells us, what does our agenda tell us? It's the end of day 2. It says summary and future work for events. So I think
we could also do that comments? At the begin. We could do that at the beginning of tomorrow too, if people have need a little time to think about that.
That would be good, and it would also, we're 19 out of, perhaps we had a peak of 30 yesterday and today, but perhaps to kind of refresh everybody's memory. First thing tomorrow, because tomorrow we start off. Well, it's to start off with summary day 1 and 2, right? So that would be actually probably a pretty good thing. So.
Right.
So any final comments before I think we all go and have a much deserved rest?
I would say enough is enough.
Yeah, right. just to remind people again, just what coming up tomorrow is that when we put this together, block 1 was, as Graris said, trying to pull all the threads together and make some concrete plans to do what seemed to be low-hanging fruit from what we had talked about, okay? And so I hope that we can have that discussion tomorrow after we've had a bit of time to ruminate on it. And the second part was the what the heck is that session right after the break, where we get to confuse each other or say that doesn't make any sense. And then I think we were going to wrap up the workshop and kind of talk about next steps for the whole thing in general. So plenty more to discuss tomorrow. But you've hung in here for 2 whole days, which is absolutely fabulous. And Gareth is like having to cut us off for day 2, which is pretty amazing. I mean, we've been going for a long time here.
It's true, yeah. It's just such a rich topic.
And Emma gets the award once again for time zones.
Yeah, it's close to 4
Aww.
So don't complain, Phil. Okay, don't complain. It's only.
Did you hear me complaining? I'm not complaining.
No, just in case. Just in case.
All right. Good night, guys. Thanks so much.
Good night, everybody.
Bye.
Good night.
We see you for summit tomorrow.
Yep. Have a great